Imagine yourself holding a coin, but instead of landing as heads or tails, it remains both at once, suspended in possibility. This is the mystery of quantum superposition, a cornerstone of modern physics. At the smallest scales of reality, particles do not rest in one clear state. An electron can be in two positions, a photon can travel through two paths, and only when an observation is made does the outcome appear fixed. Until then, reality seems to hover in uncertainty, layered with all possible outcomes. In daily life, we rarely feel this uncertainty because the world around us behaves in stable patterns. A candle burns, smoke rises, and time passes in familiar rhythm. Yet, at the quantum level, the rhythm is stranger. Imagine a medieval scholar copying a text by candlelight. To him, the flame is steady. But if he could shrink to the size of the particles dancing in that flame, he would see them as flickering possibilities, existing in many states at once, their certainty appearing only when he looked closely enough. Culture has often reflected this puzzle, even unknowingly. Folktales describe creatures that are both present and absent, doors that are open and closed until you cross their threshold. In more recent times, the famous thought experiment of Schrödinger's cat illustrated superposition vividly. A cat sealed in a box is imagined both alive and dead, its fate tied to quantum uncertainty, resolved only when the box is opened. It is not that the cat itself splits in truth, but that our understanding of outcomes is limited by the nature of measurement. The social and philosophical consequences ripple quietly. If at the deepest level of reality things exist in layers of possibility, then the world you experience is not as fixed as it appears. Each observation is like choosing a single thread from a vast tapestry, while countless others remain unobserved, untraveled, yet woven into the same fabric. As you drift on this thought, you may find comfort in its gentleness. Life feels solid, yet beneath it hums a quiet mystery, where reality itself may be more fluid than it seems. Imagine standing by the sea, watching waves roll steadily toward the shore. Each crest rises, falls, and merges into the next, continuous and unbroken. Now imagine instead a handful of pebbles, each distinct, each with its own place and shape. It seems natural to think of these two images as separate, waves on one side, particles on the other. Yet in the strange world of physics, light and matter refuse to choose. They behave as both, revealing a dual nature woven into the fabric of reality. For centuries, people argued over what light truly was. Some saw it as a wave, spreading in ripples through space. Others insisted it must be particles, tiny bundles darting from one place to another. The truth emerged in experiments that defied intuition. When passed through a narrow slit, light produced patterns of interference, just like water waves overlapping in rhythm. But when observed more closely, that same light appeared as discrete photons, individual quanta that landed like tiny footsteps on a screen. Both images were correct, yet neither told the full story. The mystery deepened when matter itself revealed the same secret. Electrons, which we often picture as tiny particles, also produced wave-like patterns when guided through similar experiments. The ordinary matter that makes up your body and the objects around you carries within it this hidden duality, switching between wave and particle depending on how we look. Imagine yourself holding a coin that is heads and tails at once, only revealing one side when you decide to look. Wave-particle duality is like that coin, hovering between forms until an interaction collapses it into something we can observe. To live in this universe is to exist in both stories at once, as solid particles that can be touched and measured, and as subtle waves that spread out, overlap, and connect. The world you see is only one version of what reality allows. Imagine yourself standing before a mirror that doesn't simply reflect your body, but your choices. Every path you might have taken extends outward, like a hall of reflections. You turned left instead of right this morning, but in another world, another version of you stepped the other way. This is the idea behind quantum mirror worlds, the suggestion that each unmade choice, Each possibility left untouched may still exist, but elsewhere. Instead of being erased, these moments split, creating parallel branches where reality plays out differently. Daily life becomes the stage for this thought experiment. Picture someone in the 14th century, deciding whether to follow their family's trade or join the clergy. In our timeline, they may have spent their years binding manuscripts in a workshop, their hands thick with the smell of ink and leather. But in another possible thread, they walked into the monastery, rising slowly in the rhythm of bells, candlelight, and chanting. Two lives, two versions of history, both rooted in one decision. Culture and story often carry this idea in gentler forms. Folklore speaks of crossroad spirits who show you the roads not taken, while modern literature explores what-if worlds, tales where one small shift changes entire destinies. Scientists, too, step quietly into the conversation. In quantum physics, particles do not always settle into one state until observed, hinting that multiple possibilities might be real at once, hidden from us by the narrow keyhole of perception. As you drift through this idea, notice the repetition: choice, reflection, branching. The rhythm of your own life feels steady, yet somewhere, if the theory holds, another you lingers in quiet, reading different words, following another thread. Whether this is truth or only metaphor, the mirror world remains a soft reminder that possibility is never truly lost, only scattered across the unseen corridors of reality. Imagine yourself watching ripples form across a still pond. Whether the stone falls in today or yesterday, the circles of water expand in the same way. In physics, certain quantum equations behave just like those ripples. They make no distinction between running forward or backward in time. This property is called time reversal symmetry, and it quietly challenges our everyday sense that time only flows in one direction. In our lives, moments feel stacked like stepping stones, one after the other, always forward. Yet beneath that sense of order, mathematics suggests a mirror-like balance. The equations that govern particles at the smallest scales do not insist on an arrow of time. They work equally well if events were to unfold backward, if every interaction could be rewound like a film. A photon of light striking an atom, or an electron shifting in its orbit, could be described with time running either way. The mathematics does not protest. And so we are left with a puzzle. Why do we feel the future approaching and the past slipping away when the underlying laws remain neutral? Physicists often point to entropy, the gradual drift from order to disorder. A cup of tea cools on the table, never the reverse. Shattered glass does not leap back together. These processes remind us that time has direction, not in the equations, but in the messy reality of countless particles colliding and dispersing. Entropy gives us the arrow of time, yet it is not written into the most fundamental rules. Imagine the universe as a vast tapestry, its threads woven forward and backward at once. Our perception of one-way flow may be no more than a habit of scale, the way human eyes notice patterns but miss the smallest details. To the equations, the future and the past are reflections of each other. To us, they remain separate shores, joined only by memory. Imagine two particles, born together in the same instant, then flung to opposite ends of the universe. One drifts near a dying star, the other hums quietly in a laboratory on Earth. Yet, if you measure the spin of one particle, the other responds instantly, as if connected by an invisible thread that stretches beyond the limits of space and time. This is the paradox of quantum entanglement, a phenomenon that unsettled even Albert Einstein, who famously dismissed it as spooky action at a distance. To understand the strangeness, picture yourself in a quiet village centuries ago. Daily life followed predictable rhythms, markets opening with the sun, church bells marking the hours, and travelers carrying messages that took weeks to arrive. Communication was slow, bound by distance. Now compare that with entanglement, a kind of message that arrives not in weeks or days, but in no time at all. It challenges the very structure of causality we've built our world upon. In the 20th century, experiments began to test whether this invisible link was real. Scientists like John Bell crafted mathematical proofs showing that entangled particles defy the logic of local realism, the idea that objects have definite states independent of observation. Later, laboratories in Geneva and Vienna confirmed it with photons traveling kilometers apart, their properties still mirroring each other perfectly. Even when separated by great distances, the outcome of one measurement determined the other, faster than light itself could travel. What does this mean for daily life? Imagine writing in your journal, and at that exact moment, someone on the far side of the planet writes the same words without knowing why. It feels impossible, yet this is the scale of correlation entanglement implies. No signal is exchanged, yet order emerges from separation. Some see in this mystery a glimpse of hidden unity, that the universe may be less a scattered collection of parts and more a single, indivisible whole. Others view it as a reminder of how much remains unknown. Like a quiet hum beneath ordinary life, entanglement suggests that reality itself is stitched together by threads we cannot see, but which pull taut the instant we look. Imagine yourself standing beneath a vast tree, each branch splitting into smaller branches, and those into even smaller ones, until the horizon disappears into an endless web of possibilities. This image lies at the heart of the infinite many worlds theory, the idea that every possible choice, every potential outcome, plays out somewhere in an expanding multiverse. In the world you know, you are here, listening. But in another, you may have chosen differently, and your day has unfolded along another path. The theory suggests that nothing is ever lost, only shifted into a parallel thread of reality. To bring this into daily life, imagine a merchant in medieval Florence standing at the market gates. He considers whether to sell wool or to travel with spices brought across long and dangerous routes. In one branch of reality, he stays in the city, his hands thick with the scent of dye and fabric, living a steady life. In another, he sets out on the road, crossing deserts, eating from small fires, and perhaps never returning. Both lives are real, but each unfolds in its own universe, never touching the other except at the single moment of choice. Culture, myth, and philosophy have long reflected this fascination with the other path. Folklore tells of mirrors that show you not your reflection, but the life you would have lived had you chosen differently. Ancient philosophers pondered the idea of fate as a braided rope, strands bound together, yet pulling in many directions at once. Today, physics translates these old intuitions into quantum theory, suggesting that particles themselves do not collapse into one state, but stretch across many until observed. The rhythm of uncertainty at the smallest scale becomes a rhythm of possibility across the whole universe. As you drift with this thought, notice its quiet repetition, branch upon branch, path upon path, each as close as your own reflection, each as unreachable as a dream fading at dawn. The infinite many worlds theory does not ask you to prove it, only to imagine its calm expanse, where every possibility continues, and where your own life is only one thread in an endless unfolding tapestry. Imagine yourself staring into what appears to be pure emptiness, the kind of space between stars or the still air between objects in a quiet room. It feels silent, without substance, if there is truly nothing there. Yet physics reveals that even the deepest vacuum is never truly empty. Instead, it is alive with tiny flickers, particles that appear and disappear in less time than it takes for light to cross the width of an atom. They are called virtual particles, and though they cannot be captured or held, their brief existence shapes the universe in ways that are both subtle and profound. Think of space not as a blank canvas, but as a restless surface of water. Even on a day that looks calm, ripples move beneath. In the same way, the so-called vacuum hums with fluctuations. Pairs of particles and their opposites rise out of the background energy, cancel each other, and fade back into nothingness. These moments are fleeting, invisible to the eye, yet their effects can be measured. A striking example is the Casimir effect, where two metal plates placed very close together are gently pushed toward one another, not by air or magnetism, but by the imbalance of virtual particles between them. Something from nothing produces a force that can be weighed in the laboratory. Even the stability of atoms carries their touch. Electrons do not orbit quietly, but shift in subtle ways because of interactions with these flickers. The delicate fingerprints of elements, the light they emit when excited, are shaped in part by the invisible dance of particles that never fully exist. And near the edge of a black hole, these same fluctuations may create what we call Hawking radiation, one particle falling inward, the other escaping, allowing the black hole itself to lose energy over unimaginable spans of time. So when you imagine empty space, try not to picture a void. Instead, see a restless ocean of fleeting presences, appearing and vanishing like whispers too soft to hear, yet powerful enough to guide the evolution of stars, galaxies, and even the atoms that make you. The silence of the universe is never silent at all. It is filled with the constant flicker of possibility. Imagine standing in front of a solid wall, its surface firm, unmoving, the kind of boundary that leaves no question about what lies on either side. In everyday life, such obstacles must be climbed, broken, or walked around. Yet in the strange world of quantum mechanics, particles don't always respect these limits. Instead, they sometimes appear beyond barriers without ever breaking them, as though slipping quietly through a hidden door. This curious behavior is called quantum tunneling, and it unsettles the rules we take for granted. At its core, tunneling happens because particles are also waves of probability. An electron approaching a barrier doesn't stop abruptly. Its wave spreads and lingers beyond the wall. Most of the time, the particle is reflected back, but every so often, there is a chance it is discovered on the far side, having passed through without crossing in any ordinary sense. To the human imagination, it feels like watching a shadow glide past stone while the object remains behind. Far from being rare, tunneling shapes much of the world you know. In the heart of the sun, protons rely on it to fuse together, creating the energy that warms our planet. Without tunneling, the skies would be dark. On Earth, microscopes use the same principle to reveal the outlines of individual atoms, turning the invisible into something observable. It is a reminder that barriers, however absolute they appear, may not be final. Even in the smallest scales of nature, there are quiet passages that allow the impossible to unfold, not through force, but through probability. Imagine yourself in a quiet room, the air still, a clock ticking softly in the corner. You think of observation as something passive, like opening your eyes to what is already there. Yet, in the strange depths of physics, observation is never neutral. Measuring something can alter its state, leaving you with a reality that would have been different if you had simply chosen not to look. This is the observer effect, and its most haunting example lives in the double-slit experiment. A beam of particles is sent toward two narrow openings. Left unmeasured, the particles create a pattern of waves, as if each particle drifted through both slits at once. But the moment a detector is placed to watch which slit it travels through, the pattern collapses. The wave becomes a particle. Possibility folds into certainty, as though reality itself waits for attention before deciding what form to take. This is not only a laboratory curiosity. You can glimpse echoes of it in daily life. A craftsman shaping wood with no one nearby may move slowly, breathing into the rhythm of his work. But place a visitor at his shoulder, and the flow changes. His movements sharpen. His posture stiffens. In classrooms, workers' quarters, or open marketplaces, people behave differently under a watchful gaze. The ancient Roman satirist Juvenal once warned that, "Who will guard the guards themselves?" For him, it was a question of power, but beneath it lies a quieter truth. To be watched is to be changed. The observer effect, then, is not only physics nor merely psychology. It is a reminder of the fragile relationship between what is and what is seen. You may wonder, when you are not looking, does reality drift in a haze of probabilities? Or is it fixed, simply hidden from your view? The answer remains unsettled. Yet perhaps the act of observation, in science and in life, is less about uncovering truth and more about weaving yourself into the fabric of what you observe. To watch is to touch, to measure is to alter. And in that small but inescapable disturbance, you become part of the story you thought you were only witnessing. Imagine standing in a room completely empty, lights off, temperature absolute zero, nothing stirring. You might think you've reached the purest silence of existence, a void where no vibration, no particle, no flicker of movement remains. But the strange truth is that even here, in absolute stillness, reality hums. Beneath the surface, there is a restless sea of energy, a background buzz so faint we cannot touch it directly, but powerful enough to shape the very structure of the universe. Physicists call this the zero-point energy field. It is the lowest possible state of energy, the baseline below which existence itself cannot go. Imagine a violin string held so tightly still you would think it rests in silence, and yet, on a microscopic level, it still trembles with a hidden motion. The cosmos is like that, never entirely quiet. The concept first unsettled scientists when they realized that quantum rules did not allow for a true vacuum. Even when you strip matter away, particles emerge for fleeting instants, collide, and vanish again. This constant flickering is not metaphorical. It has been measured in subtle effects, such as the Casimir experiment, where two uncharged plates, placed very close together, are pushed by invisible forces generated by these quantum fluctuations. The plates are nudged not by air or magnetism, but by the pressure of space itself. You begin to see how nothing is never really nothing at all. Daily life seems far from such mysteries, yet each lamp, each GPS signal, each microchip rests on physics that acknowledges this restless background. Engineers dream of tapping into it, of one day drawing usable energy from the field, though so far it remains only a dream. Still, the thought lingers. Even when you feel you've reached silence, when you close your eyes in darkness, when the world seems paused, there is motion, there is vibration, there is energy humming invisibly beneath it all. The universe, in its quietest state, is never truly at rest. Imagine yourself watching a single droplet of oil move slowly across the surface of water. At first glance, it seems random, but then you notice the gentle ripples guiding it, invisible currents that shape its path. This image captures something of the pilot wave theory, an interpretation of quantum mechanics suggesting that particles are not wandering freely in chaos, but instead are being quietly steered by hidden waves. Unlike the well-known idea of superposition, where particles seem to exist in many states at once, this view offers a different rhythm. A particle always has a definite position, but its journey is directed by an unseen guide. To imagine this in daily life, picture a craftsman in the 17th century, cutting glass for an early telescope. To him, each shard falls in its own unpredictable way. Yet beneath the table, subtle drafts of air and the slope of the floor gently nudge their course. In a similar manner, pilot wave theory suggests that electrons, photons, and other quantum particles move along hidden currents, guided by what physicist Louis de Broglie once called pilot waves. Cultural echoes of this idea have existed for centuries. Sailors once trusted the pull of tides and winds they could not see, charting courses across oceans on faith in invisible forces. Folklore too often described unseen spirits that directed human lives, not through visible intervention, but through subtle shaping of circumstance. In the same way, pilot wave theory proposes a reality that feels both tangible and elusive, a world where certainty exists, but only because of pathways traced beneath our perception. For modern science, this interpretation removes some of the unsettling mystery of quantum collapse. Instead of outcomes splitting into countless worlds, each particle follows one path, quietly choreographed by its guiding wave. Yet this theory is not without debate. Some physicists embrace it as a return to determinism, while others dismiss it as an unnecessary layer. Still, as you sit with the thought, it offers a calm reassurance. Even in the smallest structures of nature, there may be hidden currents, subtle rhythms that carry each particle forward. And perhaps, by extension, each of us is carried too, along paths that seem random only because we cannot see the waves beneath. Imagine yourself sitting in a quiet room, the walls still, the air unmoving. You trust this stillness because the rules of nature feel constant. Gravity pulls, light travels, matter behaves in familiar ways. Yet physicists remind us that beneath this calm is something more fragile than we imagine. The vacuum of space, the apparent foundation of reality, may not be absolute. It could be a state that is stable only for now. A false equilibrium. If disturbed, even slightly, the vacuum could slip into a lower state, rewriting the laws of physics everywhere at once. This is called quantum vacuum decay, a possibility that sounds like science fiction, yet emerges naturally from equations we use to describe the universe. The idea begins with the vacuum itself. Empty space is not truly empty. It hums with hidden energy, fluctuations of quantum fields that never fully settle. What we call the vacuum today may only be a temporary arrangement, like a ball resting in a shallow valley. From a distance, the ball looks at rest, but a small nudge could send it rolling into a deeper valley nearby. If the vacuum were to shift in this way, the constants of nature, the strength of forces, the masses of particles, could change instantly. Atoms might no longer hold together, light might not travel the way we know, and chemistry itself could vanish in an instant. This shift, if it happens, would spread at the speed of light, a bubble expanding outward, rewriting everything it touches. There would be no warning, no sign, no chance to see it coming. The comforting order of physics would dissolve, not through violence, but through a quiet reconfiguration of reality's most basic rules. Though unsettling, this possibility is not meant to alarm. It reminds us that what feels permanent may be provisional, that stability itself is a kind of illusion. For now, the vacuum holds steady, and the familiar rhythm of the universe continues. But within the silence of space, the question lingers, whether the foundation we walk upon is the true ground or only a temporary pause in a deeper, shifting landscape. Imagine pausing for a moment before making a choice, perhaps lifting a cup of tea, or deciding whether to glance out the window. In daily life, these moments feel like small acts of free will, tiny proofs that the future is still open. Yet the hypothesis of superdeterminism suggests something far more unsettling. It proposes that every choice, every movement, every thought was already encoded in the fabric of the universe long before you were aware of it. What feels like freedom may simply be the unfolding of a pattern too vast for us to see. The roots of this idea lie in the puzzles of quantum mechanics. Experiments with entangled particles seem to show that outcomes are not random, but strangely correlated, no matter the distance. For many, this hints at hidden connections beyond space and time. But superdeterminism takes it further. It suggests that not only the particles, but also the experimenters themselves, including their choices about what to measure, are part of a predetermined web. Nothing is excluded, not even the decision to test the theory in the first place. To imagine its reach, picture a village where every path has already been drawn on the map, even before the travelers set foot on the road. The journey feels personal. The turns appear deliberate, but every step only fulfills what was marked long ago. The unsettling comfort of superdeterminism is that it erases uncertainty. If true, there are no accidents, no alternate possibilities. The universe is a single script, written in the language of physics, and you are one of its sentences, carried forward without pause. Imagine yourself walking through a quiet corridor lined with mirrors. Each step you take reflects back, stretching into infinity, yet always repeating the same image. In physics, there is a concept just as haunting: quantum recurrence time. It suggests that given a vast enough span of time, every state of the universe could eventually repeat, exactly as it once was. The arrangement of atoms in your body, the pattern of clouds in the sky, even this very moment of you listening, all could return, not as memory or imitation, but as a precise replay, indistinguishable from the first occurrence. The idea traces back to the Poincaré recurrence theorem, born in the late 19th century, when mathematics began to unravel the strange rhythms of dynamical systems. Imagine a finite collection of particles, like grains of sand in a sealed hourglass. Stir them long enough, and despite the countless variations, the laws of probability dictate that their arrangement will, eventually, recur. The timescale for this return is so immense, often exceeding the lifespan of stars or even the universe itself, that it becomes less a prediction than a meditation on eternity. Still, the principle remains. Repetition lies hidden in the heart of chaos. Daily life offers faint analogies. Think of music drifting through a village square, the same festival returning each year, the same dances, the same voices, slightly altered but familiar. Or consider the turning of the seasons, when spring returns with its blossoms, not identical but echoing the past so closely it feels like memory. These cycles hint at the comfort and strangeness of recurrence, though on a human scale they are shadows of what physics proposes. The deeper mystery rests in time itself. If recurrence is inevitable, does it mean history is bound to repeat endlessly, each of us living the same lives again and again, unaware of the loop? Or is recurrence a mathematical ghost, never truly reached because the universe may end before its patterns can return? No one can say for certain. But as you imagine yourself walking through that mirrored corridor, each reflection folding back into the next, you begin to sense the quiet suggestion. Perhaps every moment you live is not the only time you live it. Perhaps, somewhere in the unimaginable expanse of time, it will return, unchanged, waiting for you once again. Imagine you roll a pair of dice. You expect certain numbers to appear more often than others, and probability gives you the map to predict that pattern. In everyday life, probability feels like common sense, grounded in experience. But in the quantum world, probabilities follow a rule that does not emerge from intuition or experience, but from the strange mathematics of wave functions. This is the Born rule. It tells us that the chance of finding a particle in one place or another is not given by the wave itself, but by the square of its amplitude. A subtle adjustment, but one that reshapes the entire way reality unfolds. Without this rule, the predictions of quantum mechanics would collapse. Yet, even though it works unfailingly, we do not fully understand why it must be so. Consider the double-slit experiment, where electrons or photons pass through two tiny openings. If you asked where a single particle will land, you cannot predict it with certainty. The Born rule dictates that you take the wave describing its motion, square it, and you will obtain the probability distribution. The result matches perfectly with what scientists see on their screens as countless dots form an interference pattern. Imagine the rhythm of that unfolding, single impacts, scattered like raindrops, yet gradually weaving into an intricate design that could only have been predicted with this mysterious formula. For daily life, it may seem distant, yet the Born rule lies behind the reliability of semiconductors, lasers, even medical imaging. It is as though every technology we depend on rests upon a silent agreement between nature and mathematics, a rule that has never been broken. And still, the deepest mystery remains. Is the Born rule simply a law of the universe, written into its foundation, or does it point to something deeper, a hidden logic we have not yet uncovered? As you reflect on it, the thought lingers. Our reality might be less a solid stage and more a probability field, where certainty is forever beyond reach, yet patterns emerge with unfailing precision. Imagine yourself walking through a quiet garden at dawn. The air is cool, dew clings to the grass, and sunlight begins to filter through leaves. To the eye, this moment feels ordinary, yet hidden beneath it may be one of the most astonishing mysteries in science, that life itself could rely on quantum effects to exist at all. This is the realm of quantum biology, a field exploring whether the strange principles that guide particles, superposition, entanglement, tunneling, also shape the rhythm of living things. It suggests that your morning breath, the light in your eyes, even the beating of your heart, might be sustained by processes that operate at the very edge of our understanding. Take photosynthesis as an example. When plants absorb sunlight, they must transfer energy with remarkable efficiency, almost without loss. Classical physics struggles to explain how they do this so perfectly, but quantum biology proposes that plants may use superposition, allowing energy to explore multiple pathways at once until it finds the most direct route. Imagine a traveler standing at a dozen roads, not choosing one, but briefly walking them all, and instantly arriving by the fastest. Other mysteries hint at the same. Birds, such as robins, appear able to sense the Earth's magnetic field during migration, navigating thousands of miles with uncanny precision. Some researchers believe this may be explained by quantum entanglement within specialized proteins in their eyes, allowing them to see magnetic fields. Even human senses might contain echoes of this hidden order. The sharpness of smell, the complexity of vision, and the timing of biochemical reactions may all rest on delicate quantum events unfolding within us, unnoticed. Though much remains uncertain, the thought itself is calming, that life is not separate from the strangeness of the universe, but deeply woven into it. Just as particles follow hidden rules beyond sight, so too might living things. As you drift with this idea, imagine your own body as a quiet garden of quantum effects, each heartbeat and breath guided by forces subtler than light, carrying you gently through the mystery of being alive. Imagine yourself looking up at the night sky, stars scattered across a dark canvas, each one feeling like a distant point separate from the others. Our daily lives reinforce this sense of separation, one stone distinct from another, one thought following the next. Yet quantum cosmology asks us to set aside this picture and consider something stranger, that the entire universe itself may be a single quantum object, indivisible, described not by individual pieces but by one vast wave function stretching across all of existence. In quantum mechanics, a particle is never simply a point in space. It exists in a cloud of possibilities, described by a wave function that tells us not where it is, but where it might be. This strange, probabilistic description has been confirmed countless times in the laboratory, from electrons interfering like waves to atoms existing in multiple states until measured. Quantum cosmology extends this principle outward. If it applies to the smallest of particles, why should it not apply to the universe itself? The suggestion is that our cosmos may not have a fixed history. Instead, it could be suspended among many possibilities at once, a cosmic superposition. Observations, the act of galaxies forming, stars burning, humans watching, do not collapse this wave function in the simple sense we imagine. Rather, they are part of the same quantum fabric, branches of possibility woven into a single whole. To think this way is to set aside the familiar picture of space as empty and objects as separate, and instead to imagine the universe as a single melody, its notes inseparable from the song. For the listener, the idea is less about answers and more about perspective. The next time you notice the stillness of the night sky, imagine that you are not standing outside of it, observing from a distance, but that you are within one vast quantum object, entangled with every star and every atom. In that vision, the universe is not a collection of parts, but one shimmering whole. Imagine standing at a crossroads, deciding whether to walk left or right. The choice feels rooted in the present moment. You look, you think, you act. Yet in quantum physics, there is an experiment suggesting that your choice made now can ripple backward, altering how a particle behaved in the past. This is the essence of the delayed choice experiment, first proposed by physicist John Wheeler, and it unsettles our ordinary sense of time and causality. The setup resembles the classic double-slit experiment. Particles like photons are sent toward two slits, and their pattern depends on whether you observe them. If unmeasured, they behave like waves, spreading out and interfering. If observed, they behave like particles, taking one path. Wheeler's twist was to delay the decision of whether to measure until the photon had already passed the slits. Strangely, the outcome still reflected the choice, almost as if the photon's earlier behavior had waited for your later decision. To picture this, imagine a traveler walking down a forked road. Only after they've gone out of sight, you decide whether to place a gate behind them, forcing the story of their path to change. Somehow, the record of where they went seems to rewrite itself to match your choice, even though the action came after the event. What does this mean? Perhaps particles do not have definite histories until they are asked to reveal them. Perhaps time itself, at the quantum level, does not flow like a single arrow, but bends in subtle loops of possibility. For us, it is a quiet reminder that the past may not be as fixed as it seems, and that reality, in its most delicate layers, may wait for our gaze before deciding what it has always been. Imagine yourself in an old library, the air heavy with the scent of paper and polished wood. You open a book and expect its words to remain the same, no matter which other volumes rest beside it. In the classical world, reality works this way. An object has properties that can be measured independently of everything else. But in quantum mechanics, the story is stranger. The outcome of a measurement can depend on what other measurements you choose to perform at the same time. This is the essence of the contextuality principle. Reality is not a fixed script waiting to be read, but a performance that shifts depending on the stage you set. To see this more clearly, imagine rolling a die. In ordinary life, the number that shows up is independent. It does not matter what questions you ask alongside it. But in the quantum realm, the number that appears can change depending on which other dice you decide to roll with it. Context becomes inseparable from result. Experiments in the mid-20th century, like those inspired by John Bell's inequalities, revealed that no hidden set of properties can explain quantum outcomes without acknowledging this strange dependence. The universe, it seems, does not carry a neatly labeled box of answers waiting to be opened. Instead, the answers crystallize in relation to the questions asked. Daily life offers only pale reflections of this. A person may act differently at a family gathering than they do among colleagues, not because they are hiding a single true self, but because identity is deeply entangled with context. A melody played on a flute in a quiet chapel carries one mood, yet the same notes in a crowded marketplace become something else entirely. The tune is the same, but its meaning is altered by what surrounds it. So too, in physics, the outcome is never entirely isolated. It belongs to the setting in which it is measured. The principle of contextuality unsettles the notion of an objective, observer-independent reality. Instead, it suggests a world where measurement is more than revelation. It is creation. What you choose to measure shapes what is real, and what is real cannot be divorced from the choices you make. Imagine yourself once more in the library. Each book changes its story depending on the others you open beside it. The shelves may look silent and still, but the truths within them are not absolute. They are contextual, waiting for you to decide what will be read together and what reality will emerge from your questions. Imagine watching a particle travel through a double-slit experiment. You know the setup by now. When no one checks which slit it passes through, the particle behaves like a wave, interfering with itself and forming a delicate pattern across the screen. But the moment you measure which slit it went through, the interference disappears. The particle collapses into behaving like a solid object, as if awareness itself forced it to choose. This already bends our sense of reality, but the quantum eraser experiment goes further. It shows that even after the particle has struck the screen, the interference pattern can be restored, simply by erasing the record of which path it took. It is as though the particle's history was rewritten, as though the past only solidifies once information about it is known. In the experiment, entangled pairs of photons are created. One travels to a detector, while its twin carries information about which path was taken. If you preserve that information, the interference vanishes. If you erase it, even after detection, the interference returns. Imagine standing before the results. The dots are already printed, yet whether they show a wave-like pattern depends on a choice made afterward. It feels like causality itself is pliable, not a straight arrow, but a loop sensitive to what is known. Daily life offers no true parallel, but imagine reading a diary entry that changes depending on whether the author later burned the draft or kept it. The words remain on the page, yet their meaning shifts based on knowledge elsewhere. For physicists, this is not just metaphor. It is a reminder that quantum mechanics does not track particles in isolation, but information about them. The universe seems less like a chain of events and more like a web of possibilities, with knowledge acting as the thread that ties them into shape. And so the quantum eraser leaves us with a disquieting thought. The past is not fully fixed until the story of it is chosen. Imagine yourself standing beneath a night sky, stars scattered like grains of salt across velvet darkness. You look up, and in that simple act of observing, you become part of the scene. Wheeler's participatory universe is built on this haunting suggestion that the universe does not simply exist independent of us, but that observation itself may play a role in bringing it into being. The idea is not that the cosmos waited billions of years for humans to appear, but that reality, at its deepest quantum level, requires interaction, requires the presence of an observer, for its possibilities to collapse into a single, unfolding story. Consider the double-slit experiment, where light behaves as both a wave and a particle until it is observed, at which point it chooses one form. For Wheeler, this raised a deeper question. What if the same principle applies not just to particles, but to the fabric of the cosmos itself? Imagine walking through an empty medieval hall lit by candlelight. The space feels silent and uncertain until you step inside, your footsteps echoing against the stone. In a similar way, Wheeler suggested the universe might remain in a state of possibility until interaction completes it. Culture has always carried faint echoes of this thought. Ancient myths spoke of gods who required worship to remain alive in memory, or of stories that only existed once told. Philosophy, too, has long whispered of reality depending on perception. If no one is there to hear the tree fall in the forest, does it make a sound? Wheeler's vision stretched this riddle to its furthest horizon, suggesting that perhaps the very stars themselves are not simply passive lights, but part of a participatory relationship between cosmos and consciousness. This does not mean the universe is fragile, or that it vanishes when unseen. Rather, it suggests a more subtle rhythm. That reality is not fixed, but unfolds through the act of being noticed, recorded, remembered. As you drift with this idea, imagine the universe itself as a vast tapestry, threads woven tightly, but shimmering into clarity only when touched by the gaze of an observer. Perhaps, in the quiet act of looking upward tonight, you are not just seeing the stars, you are helping them come into being. Imagine sitting across from someone and quietly sliding a folded letter across the table. They open it, and inside are your thoughts, perfectly copied, delivered without error. Now imagine the letter never traveled at all, yet somehow your message still reached them. This is the strange logic of quantum teleportation, not the movement of matter itself, but the transfer of a quantum state, the fragile information that defines a particle from one place to another instantly. At its heart lies the phenomenon of entanglement. When two particles become entangled, they share a connection so deep that what happens to one is reflected in the other, no matter how far apart they may be. Einstein once called it spooky action at a distance. In teleportation experiments, scientists use this link as a channel. By carefully measuring one particle in just the right way, its quantum state can be destroyed in one location and recreated exactly in another, as though the particle's identity has leapt across space. The particle itself has not traveled, but its essence, its defining features, have been transferred. This process has already been demonstrated with photons, atoms, and even small groups of particles. In 2017, Chinese researchers famously teleported the state of a photon from Earth to a satellite orbiting hundreds of kilometers above. No object moved, yet the information arrived intact, proof that quantum rules can connect places once thought impossibly distant. It is not the teleportation of science fiction. No human will step into a beam and reappear elsewhere. Instead, it is something subtler, but perhaps more profound. It suggests that distance is not as absolute as we imagine, that the fabric of reality allows information to slip across its weave without passing through the space between. So when you hear the phrase quantum teleportation, think not of bodies dissolving and reforming, but of patterns of existence flowing invisibly, carried by a hidden thread of connection. Matter stays where it is, yet its essence may be written elsewhere, as if the universe keeps a second copy always waiting. Imagine sitting beside a fireplace, watching warmth drift into the room. The flow of heat feels steady and predictable. Energy moves from hot to cold, never the other way around. This is the rhythm of classical thermodynamics, the rule that defines how engines work, how food cooks, how seasons unfold. Yet at the smallest scales, where quantum mechanics governs, this rule begins to blur. Heat and energy can behave in ways that defy the expectations of ordinary physics, creating a world where the arrow of thermodynamics twists in unfamiliar directions. In this domain, energy is not a smooth stream, but a collection of tiny, discrete exchanges. A single atom can absorb or release a quantum of heat, shifting its state in abrupt steps rather than gradual flows. Sometimes, these exchanges allow energy to move against the usual current, tiny systems where heat seems to travel from cold to hot, at least for a fleeting moment. What feels impossible in daily life becomes statistically possible in the quantum realm, where probability replaces certainty. Experiments with nanoscale devices, such as quantum dots and ultra-cold ions, have begun to probe these effects. They reveal engines built from just a handful of particles, running with efficiencies that challenge the classical limit. In some cases, fluctuations even allow such engines to surpass the expected boundaries, though only briefly, before balance reasserts itself. To imagine this, think of a stream that usually flows downhill. In the quantum world, now and then, a droplet splashes upward, defying gravity for a moment before falling again. The overall direction remains, but the details shimmer with unpredictability. For us, it is a quiet reminder that even the most solid laws of nature soften when examined closely. Beneath the steady warmth of the fireplace lies a restless undercurrent, where energy dances to rules stranger, subtler, and far less certain than the ones we know. Imagine yourself stepping into a laboratory where the air feels unnaturally still, machines humming in low rhythms like a distant choir. Here, scientists pursue one of the quietest frontiers in physics, cooling matter to temperatures so close to absolute zero that its familiar individuality disappears. Normally, atoms move restlessly, colliding, bouncing, forever in motion. But as the temperature sinks, their energy drains away. Near absolute zero, at a fraction of a fraction above the coldest possible state, something extraordinary occurs. The atoms no longer behave as separate particles. Instead, they merge into a single quantum entity, a Bose-Einstein condensate, moving together as though they were one. This strange state of matter was first predicted in the 1920s by Albert Einstein, building on ideas from the Indian physicist Satyendra Nath Bose. Their calculations suggested that under extreme cooling, bosons, particles that prefer to gather rather than exclude, would collapse into the same ground state, losing their individuality. For decades, this remained a theoretical curiosity, too difficult to test. It wasn't until 1995, in a lab filled with lasers and magnetic traps, that researchers at the University of Colorado coaxed atoms of rubidium into this elusive form. The achievement was not loud or fiery, but almost poetic. Matter, when cooled enough, whispering itself into unison. Daily life offers faint echoes of this unity. Imagine a flock of birds wheeling across the evening sky, not as separate creatures, but as one body flowing through the air. Or a choir holding a single sustained note until voices blur together, the distinction between individuals fading into harmony. In a Bose-Einstein condensate, the effect is deeper still, not a resemblance of unity, but an actual collapse of many into one. The atoms do not merely imitate each other, they share the same quantum state, as inseparable as reflections in a mirror. What makes this state so mesmerizing is its fragility. A small disturbance, a touch of warmth, and the unity dissolves. The particles scatter back into their restless independence, like ice melting into water, or a choir breaking back into individual voices. It reminds us how delicate order can be, how extraordinary patterns often live only at the edge of possibility. You may find yourself wondering what this means for reality as a whole. Does the universe hold hidden states of unity, waiting only for the right conditions to reveal themselves? Perhaps. The Bose-Einstein condensate is more than a scientific discovery. It is a meditation on togetherness. Many reduced to one, individuality fading into harmony, silence drawing motion into stillness. And like the cold laboratory where it is born, it leaves you with a quiet sense that even matter itself longs, at times, to move as one. Imagine dropping a pebble into a pond and watching the ripples spread outward. Cause leads to effect, and the arrow of time feels unshakable. The pebble falls first, the waves follow. But in quantum physics, there are hints that the arrow is not so rigid. Retrocausality suggests that events in the future may ripple backward, shaping the past in subtle, invisible ways. At first, the idea sounds like fantasy, but certain interpretations of quantum experiments leave the door slightly open. They whisper that perhaps the universe does not move only forward, but in both directions at once. Think of the double-slit experiment again. A particle seems undecided, passing through two paths until it is observed. Some researchers have wondered, what if the decision is not determined only in the present, but also by conditions set in the future? The outcome would then be a meeting point, influenced from both sides of time. Experiments with entangled particles deepen the puzzle. Measurements performed on one particle seem to influence the other instantly, no matter the distance. Could it be that the signal does not travel faster than light at all, but instead loops backward through time to guarantee consistency? Daily life trains us to think linearly. You light a candle, and only then does the room brighten. Yet imagine a future choice that gently alters the setup, so the light had always been brighter to begin with. Retrocausality invites us to consider such possibilities. It does not mean time travel in the cinematic sense, but rather a universe where past and future are woven together, neither fully independent. The mystery unsettles, yet it also soothes. If true, your life might not be a one-way track, but part of a broader tapestry where the future already leans in, shaping the path you believe you are carving alone. The present becomes a meeting point, where what has been and what will be quietly negotiate what you call now. Imagine yourself opening a manuscript, each letter carefully written, each mark part of a larger design. The quantum code of reality suggests the universe might be much the same, an unfolding script, not of ink and paper, but of quantum information. Instead of being made only of matter and energy, reality may be structured by hidden bits of data, algorithms that shape every star, every grain of sand, and every moment of your own life. Quantum theory already shows us that particles carry more than position or mass. They hold information. Before observation, this information is layered as possibility, like sentences still unwritten. Some scientists believe the universe itself may compute outcomes, reality behaving less like a solid stone and more like a process running beneath our awareness. Think of a mason in a medieval square. His chisel strikes stone in a steady rhythm. To him, it's simple work. But beneath that moment lie subtle codes, the repeating sequences of physics, the hidden patterns that ensure stone cracks the way it does. Ancient thinkers imagined the cosmos ordered by a divine script. Today, physics asks if that script is woven from quantum bits. As you reflect on this, imagine the night sky as text in a vast manuscript, every star a letter in an eternal code. Perhaps reality itself is less like an object and more like language, something quietly written, word by word, into being. Imagine yourself standing on a hillside, watching the curve of the land as it falls gently toward the horizon. Gravity feels simple here, a quiet pull guiding water downhill, keeping your feet on the earth. It is the oldest of forces, the one our ancestors sensed long before they could name it. Yet beneath its familiarity lies a puzzle that has resisted the sharpest minds of science. Gravity, described so elegantly by Einstein's general relativity, bends space and time like fabric. Quantum mechanics, by contrast, describes the jittering, probabilistic dance of particles at the smallest scales. Both theories work flawlessly in their own domains, yet together they clash. The search for quantum gravity is an attempt to weave them into one vision. Relativity paints a universe where planets trace smooth arcs, where time stretches near massive objects, and where the geometry of space itself responds to energy. Quantum theory paints a world of probabilities, particles flickering into and out of being, and forces carried by invisible messengers. The problem arises in extreme places, at the heart of black holes or in the first moments of the Big Bang, where both descriptions should apply at once. Relativity insists on smooth curves, while quantum mechanics demands restless fluctuations. Neither alone can tell the whole story. Physicists have explored possibilities. String theory imagines the smallest entities not as points, but as vibrating strings whose harmonies give rise to both gravity and particles. Loop quantum gravity, instead, envisions spacetime as woven from tiny loops, like a fabric with threads too small to see. These approaches remain unproven, yet they hint at a deeper unity, suggesting that space and time themselves may not be fundamental, but emergent, like waves rising from an ocean we cannot yet perceive. So when you think of gravity, try not to picture only the weight you feel pressing down, but also the mystery that lies beneath it. The ground you stand on, the sky overhead, the very flow of time you sense, these may all be fragments of a larger pattern still hidden from view. The search for quantum gravity is not only a search for equations, but for a language capable of describing reality without contradiction, a vision where the vast and the tiny no longer disagree, but sing together in harmony. Imagine holding a coin between your fingers, balanced and ready to flip. Before it lands, you know it could be heads or tails, both possibilities suspended in the air. Now shrink that thought down to the quantum world, where particles carry a property called spin. Unlike a coin, spin is not just one orientation waiting to be revealed. It can exist in several at once, overlapping states that only resolve when you look. This is the spin state paradox, a quiet reminder that reality at its smallest scales resists being pinned down. Spin is not rotation in the ordinary sense, but a fundamental quality of particles like electrons. In experiments, when physicists pass electrons through magnetic fields, the particles behave as if they have tiny magnetic poles, pointing up or down. Yet before the measurement, the electron is not strictly either. Instead, it is described by a wave of probabilities, a mixture of possibilities that includes both outcomes. Observation collapses this mixture, and the particle seems to choose, though the choice was never determined in advance. To picture this, imagine a traveler standing at two diverging roads, not waiting to decide, but somehow walking both paths at once. Only when someone calls out to them does one path solidify, while the other vanishes into silence. In the spin world, every measurement becomes such a call, shaping reality by the act of asking. The paradox has guided technologies we now rely on, from magnetic resonance imaging in hospitals to quantum computing, where the ability to sustain overlapping spin states becomes a tool for storing and processing information. What feels like impossibility, being two things at once, becomes the very resource of progress. For us, it is a reminder that certainty may be an illusion. Beneath the surface, the universe carries states of being layered together, waiting quietly until observed, like a coin forever turning in midair. Imagine yourself standing by a quiet pond at dawn, the surface so still that even the smallest disturbance spreads outward in soft ripples. In physics, reality itself is said to be like this. Beneath every object, every particle, every visible thing, lies a hidden field, vast and continuous. A particle, whether an electron, a photon, or something more exotic, is not a solid bead of matter as we once imagined. It is instead a ripple, an excitation in that deeper field, as though existence itself were made of vibrations spreading across an invisible surface. This idea, born in the 20th century, reshaped our understanding of matter. The old picture of atoms as tiny billiard balls colliding in empty space gave way to something more fluid. Fields are everywhere, filling all of space, even where nothing seems to exist. An electron is simply a wave in the electron field, a photon, a ripple in the electromagnetic field. Even the famous Higgs particle, discovered in 2012, was a fleeting shimmer in the Higgs field that gives other particles their mass. What looks like substance is, at its root, the quiver of something more fundamental, something that never stands still. Daily life offers pale echoes of this hidden rhythm. Think of wind passing through a wheat field, each stalk bending in unison to an invisible breath, or the faint vibrations of a violin string, which you cannot see but can hear woven into music. In both cases, the movement is not the thing itself, but a sign of something larger at work: air, energy, tension. So too in physics. Particles are only the surface traces of deeper, unseen seas. And yet, this picture raises quiet questions. If all matter is only ripples in fields, then what is the field itself? Is it substance or is it structure, an abstract stage for reality to play upon? No one knows with certainty. But in the calm of such questions lies a comfort. Beneath the bustle of daily life, beneath the shifting details of identity and change, there is the suggestion of something continuous, steady, and shared. A reminder that the smallest ripple in the quiet pond of reality is never truly separate, but always part of the whole. Imagine the image of a black hole, a vast darkness where light itself cannot escape, a cosmic prison at the edge of physics. For decades, scientists believed black holes swallowed everything that crossed their horizon, keeping it locked away forever. But in the 1970s, Stephen Hawking proposed something astonishing. Through the strange rules of quantum mechanics, black holes are not perfectly black. They leak, not torrents of fire or bursts of matter, but a faint, ghostly energy now called Hawking radiation. Over immense stretches of time, this gentle trickle could cause even the mightiest black hole to evaporate into nothing. The idea arises from quantum fluctuations, those fleeting appearances of particle-antiparticle pairs in empty space. Normally, such pairs blink in and out of existence, canceling each other instantly. But near the edge of a black hole, one particle may fall inward, while the other escapes outward. To a distant observer, it appears as though the black hole itself is slowly giving up energy, one whisper at a time. It is a process almost impossible to measure directly, so faint it would take longer than the current age of the universe to watch even a modest black hole fade. Yet, the mathematics are precise, and the concept has reshaped how we think about gravity, information, and the ultimate fate of the cosmos. In daily life, the thought feels distant. Still, you might imagine an ancient mountain, unchanging in your lifetime, but destined to erode grain by grain until it is gone. Hawking radiation is the same principle, written on a cosmic scale. What seems eternal may, in fact, be slowly dissolving. The mystery deepens with a question still unresolved. If black holes evaporate, what happens to the information they once contained? Does it vanish too, breaking the laws of physics, or does it somehow survive in the radiation? No one knows for certain. And so, every quiet thought about Hawking radiation carries a haunting echo. that even the darkest corners of the universe are not truly permanent, and that the secrets they hold may be fading into silence, one particle at a time. Imagine yourself listening to a quiet choir where every voice moves in perfect harmony, no single note drifting apart. Quantum coherence is something like this: particles acting in unison, their states linked so delicately that they behave as one. In this fragile balance, distance does not matter. Whether close together or far apart, the particles remain connected, their rhythms aligned until the slightest disturbance breaks the spell. You can think of it in daily life as walking into a medieval cloister at dawn, the air cool and still. Monks chant in unison, each voice steady, the harmony filling the stone halls. The sound feels whole, indivisible, and then, if one coughs or a door creaks, the unity breaks. Coherence at the quantum scale is no different. It explains how delicate systems, like photosynthesis in plants, move energy with almost perfect efficiency, using harmony rather than chaos. Cultural echoes of this mystery appear in stories of strings of fate or invisible threads tying beings together, suggesting that connection is strongest when undisturbed. Modern physics reminds us, though, that coherence is fleeting. A glance, a measurement, or the faintest interference can dissolve it, leaving scattered particles where once there was unity. As you drift with this thought, imagine the universe itself as a quiet harmony, fragile, easily disturbed, yet astonishing in its hidden order. Imagine yourself watching water come to a slow boil on a quiet stove. At first, it is calm, a glassy surface reflecting the room around it. Then bubbles form, steam rises, and what was once liquid shifts into vapor. We call this a phase transition, the familiar shift of matter from one form to another. Yet in the quantum world, transitions happen in ways that defy the usual rules. They do not require heat or pressure in the everyday sense. Instead, they emerge from the delicate mathematics of uncertainty, driven by fluctuations that belong only to the quantum realm. A quantum phase transition occurs not with warmth spreading through matter, but with the tuning of conditions so subtle they can change how particles relate to each other. Imagine electrons in a metal, once flowing freely, suddenly locking together to create a superconductor where resistance vanishes, or atoms arranged in a crystal lattice, transforming into an entirely new pattern, guided not by temperature, but by the quantum properties of their interactions. The shift happens at absolute zero, where ordinary motion is absent, and yet the system reorganizes into a completely different state. These transitions reveal that matter is more fluid than our senses suggest. The wood of a desk, the air around you, even the metal in the devices you use, all of it exists in states that might not be permanent, but conditional, depending on hidden balances deep within. To think of matter this way is to picture it not as fixed, but as a set of possibilities, each waiting for the right change in conditions to be revealed. So as you imagine the steady rhythm of your surroundings, remember that beneath the calm surface, the rules of matter are written in probabilities. What seems solid may, under the quiet guidance of quantum laws, shift into something entirely new, a reminder that even the most stable forms carry the potential for transformation. Imagine trying to watch a candle's flame without disturbing the air around it. The closer you lean, the more your breath flickers the light. In quantum physics, measuring a system often feels the same. The act of observing collapses its delicate state, changing the very thing you hoped to understand. Yet there exists a subtle method called weak measurement, where information can be gathered without fully forcing the system into a single outcome. It is a gentler glance, one that leaves the flame still burning. In the usual quantum experiment, an electron might be in a superposition, two possibilities at once. Measuring strongly forces it to decide, collapsing the overlap into a definite result. Weak measurement, however, nudges only lightly, extracting a trace of information while leaving the state largely intact. By repeating this process across many particles, physicists can build a picture of the underlying probabilities without ever pinning them down completely. To imagine it, think of listening at a distance to a conversation carried on the wind. Each word is faint, incomplete, But as you gather more fragments, meaning begins to emerge without interrupting the speakers. In the quantum world, these faint signals reveal strange averages, values that sometimes appear to drift outside the range of what seems possible, as though reality itself stretches under the weight of observation. Such measurements have opened paths toward understanding quantum systems in real time, even as they evolve. They blur the line between knowledge and uncertainty, showing that observation need not always destroy the mystery. Instead, it can whisper at its edges, leaving the paradox intact. Imagine yourself watching raindrops slide down a window pane. You can often guess their paths, the way gravity will pull them, the way they merge and scatter. Yet every so often, one droplet makes a sudden, unpredictable turn, as if ignoring the rules. In daily life, we assume that if we knew enough details, every outcome could be predicted. Classical physics promised this certainty, a clockwork universe where each effect had its cause. But in the quantum world, at the smallest scales of reality, events emerge with no hidden reason. Particles sometimes move, shift, or decay without any cause at all. This is the unsettling heart of quantum randomness. The most familiar example is radioactive decay. Imagine an unstable atom sitting quietly for years. Then, at a moment no one can foresee, it transforms, releasing energy. No signal precedes the event. No hidden clock counts down to the instant. It simply happens. For physicists raised in the tradition of Newton and Einstein, this was a shock. The universe, it seemed, was not a perfect mechanism, but a place where chance weaves itself into the fabric of reality. Even Einstein resisted, saying, "God does not play dice." Yet experiment after experiment showed otherwise. Dice are indeed part of the game. Daily life offers metaphors, though never true equivalents. You might think of flipping a coin or shuffling a deck of cards, but those are only appearances of randomness. With enough knowledge of air currents or hand movements, the outcomes could be traced back to causes. Quantum randomness is different. It is not the disguise of hidden order. It is unpredictability at its core. And so you are left with the gentle unease of knowing that some things happen simply because they happen. No reason, no cause, no chain to trace. Just pure chance, humming beneath the patterns of existence. A reminder that beneath the order you trust in daily life, there is a quiet, restless unpredictability, forever shaping the universe in ways no one can foresee. Imagine a beam of light entering a simple device made of two half-silvered mirrors and a pair of detectors. The setup is called a Mach-Zehnder interferometer, and at first glance it looks straightforward. A beam is split into two paths, each reflected and redirected, then recombined. If particles behaved like tiny billiard balls, you would expect them to choose one path or the other, arriving at the detectors with equal probability. But what unfolds is stranger. When the paths are open and aligned, the particle behaves as if it traveled both routes at once. The beams interfere, and one detector clicks every time, while the other remains dark. The particle seems to know about the path it never took, as though its presence was spread across both. Now imagine blocking one arm of the interferometer. Suddenly, the interference vanishes, and the particle behaves like a localized object again. The results change depending not just on where the particle goes, but on whether the other path remains available. The implication is unsettling. Reality is not determined solely by the journey of the particle, but by the entire configuration of possibilities. The mere option of another path alters the outcome. This principle is not confined to thought experiments. It is the same logic underlying quantum cryptography, quantum computing, and technologies that exploit interference for precision beyond classical limits. Yet at its heart, the Mach-Zehnder interferometer remains an elegant puzzle box. It tells us that particles do not simply move through space, they move through a landscape of possibilities, responding to conditions that may never be realized. In daily life, you might think of a traveler reaching a fork in the road. Even if they choose one path, the presence of the other somehow changes the meaning of the journey. In quantum mechanics, The traveler is not forced to pick a single road until the very end. And so, this quiet device, with its mirrors and beams, reminds us that the universe does not simply record what is, but also whispers about what could have been. Imagine yourself sitting in a quiet study, candlelight flickering against the walls, thoughts drifting like smoke. For centuries, people have wondered where consciousness comes from, what makes awareness rise from matter. The quantum brain hypothesis suggests the answer may lie not only in biology, but in quantum processes hidden deep within the brain. Instead of neurons firing like simple switches, some believe that within their microscopic structures, quantum effects could create the strange richness of thought. Consider the mind's ability to hold many possibilities at once: uncertainty, imagination, memory woven together. In this view, it resembles quantum superposition, where particles exist in layered states before settling into one. Tiny structures in the brain called microtubules are sometimes suggested as the stage where this delicate quantum play might unfold, allowing thought itself to emerge from patterns too subtle for classical physics. Cultural echoes of this mystery are old. Ancient texts spoke of the mind as a bridge between body and cosmos, something both physical and beyond measure. The hypothesis does not claim to solve that riddle, but it invites us to imagine consciousness not as an accidental spark, but as part of the universe's deeper fabric, woven from the same strange rules that guide particles and stars. As you drift with this idea, picture your own mind as both candle and flame, steady yet shimmering, perhaps lit by quantum rhythms, unfolding in silence. Imagine yourself lying beneath the night sky, the air still, the stars appearing fixed, their light drifting steadily through space. It feels eternal, unchanging, yet beneath that quiet view lies one of the deepest puzzles in cosmology, the cosmological constant. It is the energy of empty space, the subtle pressure that influences how the universe expands. Without it, galaxies might never have formed. With only the slightest change, the fabric of reality could have unfolded in a way that left no room for life. Einstein first introduced the cosmological constant reluctantly, as a way to keep the universe from collapsing under gravity. Later, he called it his greatest blunder once expansion was discovered. Yet modern physics has returned to the idea, now seeing it not as an error, but as an unavoidable feature of the vacuum itself. Even when all matter and radiation are stripped away, empty space hums with energy, a quiet reservoir that pushes the cosmos outward. This mysterious effect is linked with what we call dark energy, the force that drives the universe to expand faster and faster. What makes it unsettling is the scale. The value of the cosmological constant appears to be balanced on a razor's edge. If it were larger, the universe would have flown apart too quickly, never allowing galaxies, stars, or planets to coalesce. If it were smaller, matter would have collapsed into dense knots long before complex structures could emerge. Instead, it sits at a value so precise that life, against enormous odds, can exist to contemplate it. Some see this as evidence of fine-tuning, others as a hint that countless universes may exist, each with its own version of this constant, and we inhabit the one where conditions happen to allow observers. So when you look at the dark spaces between stars, try to imagine them not as void, but as gently alive with hidden energy, pressing outward in silence. The cosmological constant is not simply a number, it is the quiet balance that allows the universe to have the shape, the rhythm, and the possibility of life as you know it. Imagine the quiet hum of a familiar computer, its circuits flipping tiny switches of ones and zeros, building every calculation step by step. This is the rhythm of classical computing, reliable but limited by the binary language of certainty. Now imagine a machine that does not settle for 1 or 0, but holds both at once, layered in a superposition of possibilities. These are quantum bits, or qubits, and together they promise a leap beyond what ordinary computers can ever achieve. Where a classical computer explores one path at a time, A quantum computer can explore many simultaneously, like a traveler walking every fork of a road at once. When qubits become entangled, their states intertwine, allowing complex patterns of correlation that classical machines cannot easily reproduce. For certain problems, such as factoring enormous numbers or simulating the delicate behavior of molecules, the difference is not just speed, but possibility itself. Tasks that would take billions of years on today's fastest machines could, in theory, be unraveled in moments. In laboratories, these ideas take form in fragile devices cooled near absolute zero. Qubits built from ions, superconducting circuits, or photons shimmer between states, their information held delicately against the noise of the environment. Even the smallest disturbance can erase their advantage, which is why so much of quantum computing is a struggle for stability. To imagine its potential, think of medicine designed by simulating molecules with complete precision or secure communication channels built on the rules of quantum physics. What now feels like a distant dream might one day be stitched into daily life. For now, the quantum computer remains more promise than presence. A glimpse of a future where the boundaries of calculation bend in ways as strange as the particles that power it. Imagine yourself in a quiet laboratory, where a small container of liquid helium sits under pale light. At first glance, it looks like any other liquid, smooth and faintly shimmering. Yet, when cooled to near absolute zero, helium undergoes a transformation so strange it seems almost alive. It slips past the ordinary rules of matter, turning into what physicists call a superfluid. In this state, helium flows without friction, without resistance, as if the usual barriers of the physical world no longer apply. Place it in a dish, and instead of staying still, it begins to climb the walls, forming a thin film that creeps upward and outward, seemingly defying gravity. The discovery of this anomaly in the 1930s startled researchers. Helium atoms, instead of moving independently, began to act in perfect coordination, behaving as though they were one vast quantum entity. Friction, which normally slows down any flow, vanished entirely. A stream of superfluid helium could move through the tiniest cracks, circulate endlessly in a closed loop, and never come to rest. It was matter in a form that seemed closer to thought than to substance, delicate yet unstoppable. In daily life, you might think of a whisper of air passing under a door, or a thin veil of mist seeping through spaces too narrow to see. But superfluid helium is even stranger. No matter how many barriers you imagine, it finds its way through, as if boundaries mean nothing at all. Watching it, scientists realized they were looking at a quantum phenomenon made visible at human scale, something that usually hides in the invisible world of atoms and waves. The anomaly is both elegant and unsettling. A liquid that climbs walls, a substance that refuses to rest, a reminder that nature's most fundamental rules bend in ways our senses cannot easily grasp. In its quiet persistence, superfluid helium invites you to imagine a universe where matter is not bound by weight or friction, but guided instead by the strange harmony of quantum order. Imagine a secret written on a slip of paper. In the ordinary world, you could divide it into fragments, letters, numbers, or symbols, and hand them out to different people. No one person could read it alone, but if they combined their fragments, the message would appear. Quantum secret sharing takes this idea and places it into the strange language of entangled particles. Instead of ink on paper, the secret is encoded into a quantum state. That state is then distributed among multiple participants, each holding only a part. Alone, their piece reveals nothing. Together, when the entangled particles are measured in just the right way, the hidden information emerges. The method rests on the principle that entanglement links particles in ways that cannot be reduced to classical logic. Imagine 3 photons generated so that their states are inseparable, woven into a shared fabric. One photon may be sent to Alice, another to Bob, another to Charlie. If Alice tries to uncover the secret without the others, her measurements collapse into noise, meaningless on their own. But when all three compare their results, patterns align, and the encoded information comes to life. In this way, security is not just a matter of trust, but of physical law. Daily life offers no direct comparison, but you might picture a lock that requires several keys turned at the same instant. The lock refuses to open otherwise, no matter how carefully one key is handled. Quantum secret sharing extends this into the invisible world, where the keys are probabilities, interference, and entanglement. Researchers imagine future networks where governments, corporations, or even distant space probes can share knowledge this way, ensuring that no single interception can reveal the whole. The beauty lies in the calm paradox it reveals. That information itself can be both hidden and preserved, safe not by secrecy alone, but by the deep rules of reality. Imagine yourself looking up at the night sky, planets drifting across the darkness in slow, predictable arcs. To the eye, their motion seems purely classical, governed by gravity, stable and vast. Yet some scientists suggest that even these enormous bodies may carry faint echoes of quantum behavior, subtle signatures of the same rules that guide particles. Just as electrons orbit within atoms, planets themselves can be imagined as following patterns that hint at hidden quantum-like order. Think of an astronomer in Renaissance Europe charting Mars with careful notes by candlelight. To him, the orbits are precise but mysterious, numbers repeating with an almost musical rhythm. Today, physics whispers that these rhythms may reflect deeper symmetries, quantum principles extended to cosmic scales. The suggestion is not that planets vanish into superposition or entanglement like particles, but that their motions may still be shaped by the same mathematical harmony, faintly echoing quantum rules written into the fabric of reality. Cultural memory often carried this intuition long before science. Ancient thinkers spoke of the music of the spheres, a cosmic harmony where each planet played a hidden note. The quantum planetary model quietly revives that vision, proposing that the universe is not divided between the quantum and the cosmic, but connected by a single underlying order. As you rest with this thought, imagine each planet not only as a stone adrift in space, but as part of a vast quantum rhythm, steady, subtle, and endless. Imagine yourself watching dust drift slowly through a sunbeam in a quiet room. Each particle seems separate, yet the air around it is always in motion, influencing its path in ways too small for you to follow. In the quantum world, particles do not begin as distinct objects with defined positions. They begin in a haze of possibilities, able to exist in overlapping states at once, like a melody that contains many notes played together. But when these fragile states touch the wider environment, they collapse into the clear notes we call classical reality. This process is known as quantum decoherence. For a single electron or photon, quantum behavior is natural. It can be in two places at once, interfere with itself, or carry multiple values at once. But as soon as it interacts with its surroundings, air molecules, photons of light, vibrations of matter, its delicate superposition unravels. What once was a cloud of possibilities becomes a definite outcome. The mystery of why we do not see cats both alive and dead, or chairs both present and absent, is explained not by their impossibility, but by the inevitability of decoherence. The environment forces the quantum world into the shape of the classical one we inhabit. Scientists have recreated this effect in laboratories, isolating particles under extreme conditions to preserve their quantum states for brief moments. In these controlled settings, superpositions and entanglement can persist long enough to be observed. Yet the slightest intrusion, an extra photon, a small vibration, causes the fragile quantum pattern to vanish. It is as though reality cannot tolerate too much ambiguity, and the environment acts as a constant editor, insisting that one version of events must be chosen. So when you imagine the solidity of your daily world, the weight of objects, the clarity of moments, remember that they emerge from countless hidden interactions. The classical world is not separate from the quantum, but is shaped from it, like a photograph developed from faint exposure. Decoherence is the bridge that carries us from a haze of possibilities into the singular world we call real, reminding us that certainty itself is the product of constant negotiation with the environment. Imagine two coins tossed miles apart, yet always landing in perfect coordination, one heads, the other tails, no matter the distance. In daily life, such a pattern would feel like a trick, a hidden signal tying them together. In physics, John Bell set out to ask whether quantum mechanics required something even stranger. His theorem became a test of whether the universe obeys local realism, the idea that objects have definite properties and nothing can influence something faster than light. Bell showed that if particles obeyed these rules, their correlations would fall within strict mathematical limits. Yet when scientists performed the experiments, those limits were broken. Entangled particles behaved as if connected by invisible threads, with one outcome instantly shaping the other across vast distances. The results suggested that either nature is non-local, that influences stretch beyond space, or that reality itself does not exist in the definite way we imagine until it is observed. To picture this, imagine two books placed in separate libraries. Each time a page is opened in one, the same page reveals itself in the other, even without a messenger traveling between them. It is not simply coincidence, it is a coordination written into the structure of the universe. Over decades, the tests became more precise, closing loopholes one by one, until the evidence grew overwhelming. Quantum mechanics does not fit neatly within classical expectations. For us, Bell's theorem remains less a solved puzzle than a mirror held up to our assumptions. Either the universe is stitched together in ways that ignore distance, or the very act of observation reshapes what is real. In either case, the challenge lingers, quietly reminding us that the world is stranger than the stories we tell to make sense of it. Imagine yourself standing at the edge of a vast horizon where light bends and silence deepens. This is the boundary of a black hole, a place where gravity is so strong that even photons cannot escape. For decades, physicists believed that this boundary, known as the event horizon, would feel strangely uneventful. According to Einstein's relativity, crossing it would bring no sudden shock, only a slow drift into darkness. Yet, quantum theory introduces a disquieting twist, the possibility of firewalls. Instead of a gentle crossing, the edge may blaze with unimaginable energy, instantly destroying anything that falls in. This puzzle arose from questions about information. Quantum mechanics insists that information cannot simply vanish, yet black holes seem to swallow it without return. To preserve the rules of quantum theory, some scientists proposed that the horizon itself becomes violent, burning away all traces of particles and data the moment they arrive, a firewall. But this clashes with relativity, which predicts smoothness. Both theories are well tested, both deeply trusted, yet here they collide, leaving physicists caught between contradictions. Daily life offers only distant analogies. You might imagine a doorway that appears ordinary from afar, its frame polished and still, yet anyone who tries to step through finds it transformed into a wall of flame. Or think of a letter slipped into a mailbox, expected to disappear quietly into a system of order, yet instead consumed at the slot before it ever enters. Such metaphors capture only the faintest shadow of what the firewall paradox suggests. The deeper question lingers. What becomes of information in the universe? If firewalls exist, the black hole edge is no silent frontier, but a destructive blaze. If they do not, then our most trusted theories remain incomplete. Standing at this horizon of thought, you sense the quiet strangeness. The universe may hide its secrets not in the depths of black holes, but in the thin, fragile surface that marks their edge. Imagine for a moment that the world around you is not built from solid matter, but from lines of code. Every breath you take, every tree swaying in the wind, every star in the night sky could be part of a quantum simulation, an intricate program running on a system beyond anything we can imagine. The idea may sound like philosophy, yet it arises naturally from the questions of physics. Our universe behaves according to rules that can be written in mathematical equations. Rules so precise and consistent, they resemble the logic of computation. The possibility lingers. Are we observing the universe, or merely the output of something deeper, a vast simulation written in the language of quantum mechanics? Quantum computers give us a glimpse of how such a reality might work. They harness the principles of superposition and entanglement to model problems far beyond classical machines. A simple lattice of qubits can simulate molecules, interactions, even miniature versions of the cosmos. If we can create small universes inside our own, could not a larger intelligence create one in which we live? The notion is unsettling not because it dismisses reality, but because it treats reality as layered. Our fundamental world might be no more than one level of an endless hierarchy of simulations. In daily life, the thought feels abstract, yet strangely familiar. When you play a video game, your character walks through landscapes that seem real within the screen. The rivers flow, the seasons change, the physics hold steady, but only because lines of code dictate them. From within, the character could never see the wires or circuits beneath. Likewise, if our universe is a simulation, we may never touch the machinery running it. The paradox rests in its quiet implication. If reality is simulated, it does not diminish its meaning. Your experiences, your memories, your life remain real to you, just as they would in any world. And yet the idea invites reflection. Perhaps the patterns we see in physics are not only descriptions of matter, but clues to the deeper architecture holding it all together. A silent suggestion that our universe may be both real and programmed, woven from quantum threads of possibility. Imagine yourself watching ripples spread across a still pond. No matter how quickly the stone was thrown, the waves move outward at their own steady pace. In the quantum world, something similar holds true. Even the tiniest particles, shifting between states, follow what physicists call a quantum speed limit, the idea that change itself, even at the smallest scales, has a maximum pace. Think of an electron shifting from one energy level to another inside an atom. It feels instantaneous, but hidden mathematics shows there is a minimum time required, a quiet rhythm to how fast the universe allows transformation. Nothing, not even quantum transitions, can leap infinitely quickly. Just as sound has a speed through air, or light has a speed through space, so too does quantum change carry its own natural boundary. Daily life rarely reminds us of this. To a medieval clockmaker, the ticking of gears and the swing of weights revealed time's steady pull. He may not have known it, but even the atoms of his brass tools were bound by the same hidden law: no movement, no shift, beyond the limit. The mystery deepens when you realize that this speed is not about distance, but about possibility. Reality itself seems to breathe with a rhythm, never rushing, always unfolding at its allowed pace. As you drift with this idea, imagine the universe not as a race, but as a calm procession, each change arriving only when its time has come. Imagine yourself reading Alice in Wonderland, the moment when the Cheshire Cat lingers in the air. Its grin hovers without its body, a smile detached from the creature that wore it. At first glance, this is only a fantasy, a literary trick meant to amuse. Yet in the world of quantum mechanics, something remarkably similar has been observed. A particle's property, its spin, its polarization, its magnetic orientation, can sometimes appear separated from the particle itself, like the grin lingering after the cat has vanished. This phenomenon is known as the quantum Cheshire Cat. In experiments with beams of neutrons or photons, researchers have been able to guide the particle down one path while its defining property seems to take another. Imagine a photon traveling through one channel while its polarization, its direction of oscillation, appears measured in another. The particle and its trait, normally inseparable, are revealed as if they could exist apart, like the body and the smile in Lewis Carroll's tale. The effect is not about magic, but about measurement. Quantum systems are fragile, and when we design experiments to test specific aspects, we sometimes find results that appear paradoxical. The particle is detected in one place, while its property seems to influence another. The underlying mathematics of quantum theory allows for this, showing that the link between a particle and its attributes is not as rigid as our classical intuitions suggest. For daily life, such separations are unthinkable. You cannot remove the color from a painting while leaving the brushstrokes behind, nor detach the sound from a bell while still holding the metal. But on the quantum level, properties behave like patterns rather than possessions, and patterns can sometimes be teased apart. So when you recall the lingering grin of the Cheshire Cat, imagine it not only as a story, but as a mirror of reality itself, where particles and their properties may part ways, only to reunite later, reminding us that the structure of the universe is stranger and subtler than the solidity we take for granted. Imagine sitting quietly, aware of the steady rhythm of your thoughts. Each memory, each sensation, feels tied to the biology of your brain, the firing of neurons, the chemistry of cells. Yet some researchers have wondered whether consciousness might not only be biological, but quantum. If that is true, then in principle, the patterns that make up awareness could one day be transferred, not as code written in zeros and ones, but as delicate quantum information. This is the provocative idea behind quantum mind uploading. In classical computing, copying data is straightforward, but in quantum mechanics, information cannot be cloned in the usual sense. Instead, it must be transferred through processes like entanglement and teleportation, where the state of one system is recreated in another while the original is erased. Applied to the mind, this suggests that uploading consciousness would not be like duplicating a file, but more like moving the very essence of thought from one medium to another. To picture this, imagine a candle flame lighting a second wick. The glow continues, but the original flame no longer burns. In the same way, a quantum transfer of consciousness would not create two versions of you. It would preserve continuity by shifting the pattern with nothing left behind. Whether the mind itself is quantum remains debated. Some theories argue that the strange coherence of thought, its unity and fluidity, hints at quantum roots within the brain's microstructures. Others remain skeptical, grounding consciousness in classical biology. Yet the speculation opens unsettling questions. If awareness is a quantum state, then perhaps the boundaries of life and self are not fixed to flesh, but are part of a wider field of information. For us, it is both promise and paradox, the dream of transcending mortality through physics, and the haunting thought that to transfer the mind is also, in some sense, to let it go. Imagine yourself walking through an ancient hall lined with mirrors, each surface catching your reflection and sending it back with subtle distortions. In daily life, mirrors are familiar, reversing left and right, but never altering the essence of what stands before them. In physics, however, the idea of a mirror goes deeper. The mirror-matter hypothesis suggests that alongside the matter we know, there may exist an unseen twin, a hidden world of particles reflecting ours in perfect symmetry, invisible but real, layered into the same universe. The idea arose from puzzling questions about symmetry in fundamental forces. Nature often prefers balance, positive with negative, north with south, matter with antimatter. Yet in the 1950s, experiments showed that certain particle interactions violated this mirror-like order. To restore balance, some theorists proposed that a parallel realm of mirror particles might exist, interacting only faintly with our own. These particles would carry their own versions of atoms, perhaps even their own chemistry, drifting silently alongside us, detectable only through the faintest gravitational pull. Daily life offers faint echoes of such hidden companionships. You might think of walking through a crowded street, aware that countless lives unfold around you, yet forever beyond your knowing. Or imagine twin cities separated by a mist, each one bustling, each one real, but neither able to see the other. In the same way, mirror matter, if it exists, could be all around, shaping the cosmos quietly, without leaving a visible trace. The hypothesis remains unproven, yet it lingers because of its elegance. It offers a possible explanation for mysteries like dark matter, that unseen substance outweighing the stars. Perhaps what we call darkness is simply reflection, a universe doubled, half hidden. As you imagine yourself standing in that silent hall of mirrors, you sense the quiet possibility that reality too may have a reflection, close enough to touch, yet forever unseen. Imagine holding a clock so precise that it would not lose a single second over the lifetime of the universe. This is not science fiction, but the promise of quantum metrology, the use of quantum effects to push measurement to limits once thought impossible. Traditional instruments, no matter how carefully built, always carry some level of noise or uncertainty. But when you allow particles to exist in superpositions or weave them into states of entanglement, the act of measurement becomes sharper, cleaner, and infinitely more sensitive. With quantum principles, even the smallest ripples in time, space, or energy can be traced with near-perfect accuracy. At the heart of this idea is interference. When two waves overlap, the tiny shifts in their phase reveal differences smaller than any ruler could detect. In laboratories, physicists use entangled photons to measure distances so fine they approach fractions of an atom's width. Atomic clocks, based on the vibrations of electrons jumping between states, already synchronize global positioning systems. Yet the next generation of quantum clocks could track time with such precision that they reveal the slow drift of Earth's gravitational field or the hidden sway of tectonic plates beneath the continents. For daily life, this sounds remote, but its influence is quiet and steady. Imagine navigation systems so accurate they can map a city down to centimeters, or medical imaging so refined it can trace molecular structures inside the body without harm. Quantum metrology points to a future where the boundaries of measurement dissolve and uncertainty shrinks until almost nothing escapes notice. The paradox is gentle but profound. We often think of quantum mechanics as a realm of uncertainty where particles hover between states. Yet here, uncertainty becomes the very tool that sharpens our view. The same strange rules that make the universe unpredictable also allow us to measure it with unimaginable clarity, reminding us that mystery and precision are not opposites, but partners, woven into the quiet rhythm of reality. Imagine yourself watching a candle flame in a darkened room. If you glance now and then, the flame dances freely, shifting with the faintest drafts of air. But if you stare without pause, focusing on every flicker, it almost seems to hold still. The quantum Zeno effect suggests something similar happens in the microscopic world. When a quantum system is observed continuously, its natural change can be slowed or even frozen by the very act of watching. Think of an unstable particle, ready to decay into something new. Left alone, it will eventually shift. But under constant measurement, its transition hesitates, as though awareness itself holds it in place. The name recalls Zeno of Elea, the ancient philosopher whose paradoxes imagined arrows that never reach their target, motion suspended by endless division of time. Here, the quantum echo is not just metaphor, but a physical effect confirmed in laboratories. Daily life carries soft parallels. A medieval scribe copying a manuscript finds his ink dries faster when ignored, but lingers stubbornly wet under constant inspection. Of course, the ink follows chemistry, not quantum law, yet the rhythm feels familiar, observation changing what is observed. As you drift with this thought, picture reality itself pausing under a steady gaze. The quantum Zeno effect reminds us that watching is never neutral. To observe too closely is to shape, and sometimes to hold still, the very thing you wish to see. Imagine yourself tracing the delicate spiral of a DNA strand, that familiar double helix carrying the instructions for life. At first, it feels solid, a molecular ladder built with dependable rungs of chemical bases. Yet at its core, DNA is not only chemistry, it is also a stage where quantum effects may quietly shape the future of living things. One of the most intriguing possibilities is quantum tunneling, where particles slip through barriers they should not be able to cross, influencing mutations in the very code of life. In classical terms, a particle should remain confined unless it has enough energy to climb over a barrier. Yet quantum mechanics allows another path. The particle can sometimes pass through the barrier itself, appearing on the other side as if it had dissolved and reformed. Inside DNA, the hydrogen atoms that link base pairs may tunnel in this way, shifting their positions unexpectedly. When they do, they can cause a mismatch, adenine pairing with cytosine instead of thymine, for instance, leading to a mutation in the genetic sequence. Such events are vanishingly small and fleeting, yet over time, they may play a role in the evolution of life. The idea that quantum effects, usually reserved for electrons and photons in laboratory experiments, could influence biology suggests that the boundaries between physics and life are less clear than we once believed. The randomness of mutations, the raw material for evolution, may be seeded not only by chemical accidents, but by quantum uncertainty itself. Imagine then that every living being, every tree and bird and human, carries within its cells a whisper of quantum strangeness. The slow rhythm of growth and change, the branching of species over millions of years may all be touched by particles tunneling in silence through DNA. Life, in this vision, is not only a biological story, but also a quantum one, where existence evolves through rules written in probabilities and quiet crossings that should have been impossible. Imagine sitting at a desk, looking at a coin resting in your hand. You know it has a definite state. It is either heads or tails, even if you aren't looking. That assumption, called realism, feels natural in daily life. But in quantum physics, experiments testing the foundations of reality suggest that things may not be so simple. And yet, even as these experiments grow more precise, they still leave gaps, loopholes, that prevent us from saying with certainty what reality truly is. One of the most famous examples comes from tests of Bell's theorem, where entangled particles appear to influence one another instantly across vast distances. The results seem to rule out local realism, yet each experiment can be questioned. Perhaps detectors miss some of the particles, or random number generators used in the tests are not truly random. Over time, physicists have closed many of these loopholes, yet new ones quietly emerge, like cracks in a surface that never fully smooths. To imagine this, picture a village court trying to decide a case with missing witnesses. Each verdict feels close to final, yet one unanswered question leaves just enough room for doubt. In the same way, quantum experiments edge closer to clarity, but loopholes keep the mystery alive. For us, this is less about flaws and more about humility. Reality at its smallest scales resists being pinned down, slipping past our instruments with quiet defiance. Each experiment narrows the possibilities, but none yet erase them all. The loopholes remain, whispering that the final word on reality has not been spoken, and perhaps never will be. Imagine yourself gazing at the surface of a simmering pot, where bubbles form, rise, and vanish in constant motion. Each bubble holds its own small world of water and air, fragile yet distinct. In physics, some theorists suggest that reality itself may resemble such a surface. The universe you know, stars, galaxies, and your own quiet life within them might be only one bubble in a vast quantum foam, surrounded by countless others, each with its own laws, its own possibilities, its own histories unfolding unseen. This picture arises from attempts to unify quantum mechanics with cosmology. At the smallest scales, space-time may not be smooth, but restless, fluctuating with uncertainty like a frothing sea. Out of this sea, entire universes could emerge, each bubble separating, expanding, and drifting into its own infinity. Our cosmos, with its familiar constants and forces, might simply be one fortunate outcome of that endless bubbling, a single stable froth in a vast, unending foam. Daily life offers gentle metaphors for this hidden abundance. You might think of villages scattered across distant valleys, each with its own traditions, unaware of the others beyond the ridges. Or picture countless lanterns floating across a dark river, each glowing softly, each unaware of the many lights drifting nearby. They share the same water, the same night, yet remain apart. In the same way, our universe may be but one fragile lantern, burning in a cosmic sea of countless others. The notion is less a prediction than a reflection on possibility. It reminds us that what feels solid and singular may instead be fleeting, one ripple among many. As you imagine the gentle bubbling of foam on water, you sense the quiet suggestion. Perhaps reality itself is not a single story, but a chorus of universes, each rising, each fading, all part of a deeper sea without end. Imagine a world described not by solid objects, but by possibilities. A particle, before you look at it, is not here or there, but both, spread out like a mist of chances. This is the wave function, the mathematical cloud that captures everything the particle could be. Yet the moment you measure it, the cloud collapses into one outcome. The paradox is simple but haunting. What causes this collapse? Physicists have debated it for nearly a century, and no consensus has emerged. One view, called the Copenhagen interpretation, suggests the act of measurement itself forces the wave function to choose. Reality hardens only when observed, as if the universe waits for our gaze. Others argue the collapse is only apparent. In the many worlds interpretation, every possibility actually happens, branching into parallel universes while we simply experience one branch. A third approach, objective collapse theories, claims the wave function is unstable and will fall into a definite state after a certain time or under certain conditions, no observer required. In this view, collapse is a physical process, woven into the fabric of the universe. Daily life seems far removed, but you can imagine tossing a coin into the air. For you, it lands heads or tails. Yet in quantum mechanics, the coin is spinning in every possible way until something resolves it. Is it your glance that finalizes it? Or is there an unseen mechanism that chooses for you? The mystery deepens because collapse lies at the heart of quantum technology. Quantum computers depend on preserving superpositions before collapse destroys them. Understanding what triggers that moment may unlock entirely new physics, or reveal that our assumptions about reality have been incomplete all along. And so the debate continues. Is collapse an illusion, an act of observation, or a law of nature itself? No answer yet satisfies all. What lingers is the strange comfort of uncertainty, the reminder that even the act of asking forces the universe into form, one possibility chosen from the quiet sea of many. Imagine yourself walking through a medieval marketplace. The noise, the smells of bread and smoke, the jostling crowd, it all seems chaotic. Yet beneath it lies an unseen order, rules of trade, customs, and quiet agreements guiding what looks random on the surface. Some physicists once thought quantum strangeness might be similar, that hidden variables, invisible but real, secretly govern the behavior of particles. At first glance, the quantum world seems unpredictable. An electron can appear here or there, its path uncertain until measured. But theories of non-local hidden variables suggested there may be more at play, a deeper layer of reality that explains the apparent randomness. The term non-local points to something subtle. These hidden influences would not be confined by distance, acting instead across space instantly, as if two faraway dice always rolled in harmony, no matter how far apart they were thrown. In daily life, you might imagine two musicians separated by miles, but still playing in perfect rhythm, as though guided by an unseen metronome. Folklore often spoke of invisible threads tying people together, fate, destiny, or unseen bonds. In physics, these threads were imagined as hidden rules connecting particles. Though experiments have largely shown that many of these hidden variable models cannot explain quantum reality, the idea still lingers. Perhaps what we see is only the surface, and beneath it lies a quiet structure, an order we cannot yet measure. Imagine yourself looking at an old planetarium model, with tiny spheres circling a central sun along fixed tracks. For much of history, We pictured electrons and atoms in a similar way, tiny planets orbiting the nucleus, moving smoothly along their paths. Yet quantum mechanics tells a different story. Electrons do not travel like planets at all. Instead, they occupy regions called orbitals, where their presence is described by probabilities rather than precise tracks. And sometimes, these electrons can shift from one orbital to another without ever passing through the space in between. This phenomenon is called a quantum jump. An electron in a lower energy orbital can suddenly appear in a higher one when it absorbs a photon of light. Later, it may drop back, releasing its own photon, a flash of energy returned to the world. What makes this unsettling is that the transition does not involve traveling through the space between levels. It is as though the electron disappears from one state and reappears in another, skipping the path we would expect. Experiments have confirmed this strangeness, even allowing scientists to watch quantum jumps in real time. Instead of a smooth slide, the change is abrupt, instantaneous in a way that resists our classical imagination. The everyday world, so bound by continuity, is built upon processes that leap discretely from one condition to another, without the gradual passage we are used to seeing. In daily life, it would be like stepping from the ground floor of a building to the third floor without ever passing the second. No staircases, no elevators, no time spent in between, just here, then there. For electrons, this is not an exception, but the rule. The stability of atoms, the colors of light, the chemistry of life itself all depend on these sudden, impossible-seeming shifts. So, when you think of matter as solid and continuous, remember that at its foundation, it is built upon jumps across silence, electrons shifting places without journeys, carving reality out of leaps that unfold in ways we cannot see, yet rely upon every moment. Imagine sitting in a quiet room, the air still, the space around you feeling empty. Yet physics suggests that emptiness is never truly empty. Even in a perfect vacuum, space seethes with activity. Virtual particles flicker into existence and vanish again. Energy ripples beneath the surface, and what looks like nothing holds a restless fullness. This is the zero-point energy of the vacuum, and some have imagined that if it could be tapped, it might power entire civilizations. In quantum field theory, every field has fluctuations, even at its lowest energy state. These fluctuations give rise to effects we can measure, like the Casimir force, where two metal plates placed close together are gently pushed by the quantum vacuum itself. It is a faint but real reminder that nothing hides hidden reservoirs of energy. Extrapolated to the scale of the universe, the amount of energy in empty space appears immense, so immense that harvesting even a fraction could eclipse all other known power sources. To imagine this, think of standing by a calm sea. On the surface, the water looks smooth, almost still. Yet beneath, countless waves and currents shift restlessly, holding energies far greater than what appears above. The vacuum is like that sea, quiet to the eye but alive with hidden depths. For now, tapping this energy remains speculation. The laws of physics allow us to measure its presence but not to extract it in any controlled way. It may be forever locked beyond reach, or perhaps waiting for principles we have yet to discover. For us, it remains both a dream and a paradox. That in the silent emptiness surrounding us, there may lie enough energy to light the stars of entire futures. Imagine yourself sitting beside a fire on a quiet evening, watching wood turn slowly to smoke and ash. Even as the flames consume it, you know the information is not lost. The molecules scatter, but their record remains, written into the air, the heat, the light. Physics tells us that this is always the case. Information, no matter how disguised, cannot truly vanish. But then comes the puzzle of black holes. These cosmic abysses swallow everything, light itself included, hiding it beyond an event horizon. And here, the paradox begins. If nothing escapes, what happens to the information carried by what falls in? For a long time, scientists assumed the answer was simple. The information is destroyed. Yet quantum theory resists this, declaring that the universe does not permit true erasure. In the 1970s, Stephen Hawking showed that black holes emit faint radiation, slowly evaporating over time. If the black hole eventually disappears, what remains of the information it consumed? Is it preserved in the radiation? Is it encoded in some hidden surface at the horizon? Or does it vanish forever, breaking the very rules of physics? Daily life offers pale metaphors. Imagine a letter burned to ash. You can no longer read it, yet, in principle, every particle of smoke, every flicker of heat, still carries traces of its words. Or think of footprints washed away by the tide. To the eye, they are gone. Yet in the shifting sands and currents, their record lingers. Black holes challenge this comfort, suggesting an erasure so complete that nothing remains. No trace, no echo. The paradox unsettles because it touches the core of order in the universe. If information can be destroyed, then the laws we trust may not hold. If it is preserved, we have yet to understand how. And so black holes remain both prisons and teachers, their silent horizons asking the same unyielding question: does the universe ever forget? Or is every story, no matter how deeply buried, written forever into the fabric of reality? Imagine zooming in on the fabric of space-time itself. From far away, it feels smooth, like a perfectly woven cloth stretched across the cosmos. Galaxies glide along it, stars bend it, planets curve within it. But what if you could shrink yourself down, smaller than atoms, smaller than quarks, into the very grain of existence? At those scales, some physicists believe space-time might not be smooth at all. It may look jagged, irregular, like the coastline of a map that becomes more complex the closer you examine it. In other words, the foundation of the universe may be fractal. Fractals are patterns that repeat endlessly, shapes that reveal new detail no matter how far you zoom in. Coastlines, snowflakes, even the branching of trees show this self-similar quality. If space-time is fractal, then beneath the orderly equations of relativity lies a hidden complexity. Instead of a calm, continuous surface, the fabric of the universe might be a restless web, where distances blur and geometry twists in unexpected ways. The smallest scales could resemble a storm of patterns, endlessly nested. In laboratories, hints of this possibility appear in attempts to unify gravity with quantum mechanics. Some approaches suggest that at the Planck scale, so tiny it defies imagination, space-time may have a fractal dimension, one that shifts depending on how closely it is examined. Instead of 4 dimensions, as we experience, the universe could behave as if it has fewer at the tiniest levels, expanding into more only as scale increases. For daily life, this is difficult to picture, yet you might imagine walking along a rocky shoreline. From the air, the coast looks smooth. On the ground, every rock and crevice adds detail the map could never capture. In the same way, space-time may appear smooth from our human perspective, while at its foundation, it is endlessly intricate. The paradox is quiet, but profound. The closer you look, the less certain the ground beneath reality becomes. Space-time, the very stage on which everything unfolds, may not be simple at all, but an infinite geometry whispering complexity at every scale. Imagine yourself standing in a quiet workshop where metals are being shaped. To the eye, each material, iron, copper, or glass, seems fixed in its own state: solid, liquid, gas. The phases of matter we know well, yet in the quantum world, these phases themselves can become entangled, bound together the way particles are, sharing information instantly across distance. Instead of existing only as separate states, matter can weave connections between phases, creating patterns that defy the boundaries we take for granted. Think of water in daily life. It can freeze, flow, or rise as steam, each phase distinct. But imagine a hidden thread tying these states together, so that a shift in one quietly influences the other, no matter how far apart they are. In quantum experiments, such entanglement allows phases of matter, superfluids, superconductors, and exotic states to behave in harmony, like musicians separated by walls but playing a single song. History often hinted at this vision. Ancient thinkers spoke of the four elements as connected, transformations echoing across fire, water, air, and earth. In modern science, the echo is quieter but more precise, the possibility that the very phases of matter are not isolated, but deeply entwined through quantum rules. As you rest with this thought, imagine every shift of matter not as separation, but as part of a hidden unity, different phases whispering to each other across the silence of space. Imagine yourself holding a clear crystal in your hand, the light passing through it as though nothing is hidden within. To the eye, it seems simple, an arrangement of atoms locked into a repeating structure, silent and unchanging. Yet researchers have found ways for crystals to do something remarkable, to act as memory keepers for quantum states, holding fragile patterns of information long after they would normally vanish. These are sometimes called quantum memory crystals, and they suggest a future where matter itself may quietly remember what has passed through it. Quantum states are notoriously fragile. A particle can exist in a delicate superposition, many possibilities at once, but the slightest disturbance from the environment will collapse it into a single outcome. This is what makes quantum computing so difficult. Information carried in these states fades almost instantly, lost before it can be used. Crystals, however, offer a potential solution. By embedding quantum information into the collective behavior of atoms in a solid, scientists have found ways to extend its lifespan. The crystal, in effect, becomes a safe harbor, preserving a fleeting state far longer than free particles ever could. In experiments, researchers have used rare Earth-doped crystals to store the state of photons, keeping the delicate imprint of light for measurable stretches of time before releasing it again. Imagine a whisper caught in glass, held in silence, then returned unchanged. Such materials may one day serve as the backbone of quantum networks, where information can be transmitted, stored, and retrieved without losing its fragile quantum nature. For daily life, the image of a crystal that remembers feels almost mythic, as though matter itself could bear witness to passing events. Yet this is not a metaphor, but a real frontier of technology, where the line between memory and material begins to blur. A future shaped by quantum memory crystals would be one where information is no longer transient, but anchored in the very lattice of matter, waiting patiently until it is called upon again. Imagine looking at a photograph of a mountain and realizing the light that formed the image never touched the mountain at all. In daily life, this seems impossible. Images are made when light bounces off objects and enters our eyes or cameras. Yet in the quantum world, there exists a technique called ghost imaging, where a picture can be created using particles that never interacted with the object in question. The process relies on entangled photons, pairs of light particles born together in a quantum link. One photon is sent toward the object, but it is not recorded in detail. Its twin, which never meets the object, is measured carefully. When information from both is combined, an image of the object emerges. The surprising part is that the photon used to make the image never saw the object at all. It only carried the imprint of its partner's journey. To picture this, imagine two travelers setting out from the same village. One walks through the marketplace, seeing the stalls and colors, while the other takes a quiet path through the fields. Later, when their stories are combined, the one who never saw the market can still describe it perfectly, as though the experience was shared. Ghost imaging has moved from theory into practical experiments, producing pictures of objects with remarkable clarity. Some hope it could be used in low-light environments, or in situations where sending strong beams of light would damage delicate materials. It suggests that information can flow in ways far stranger than our ordinary sense of cause and effect allows. For us, it is another reminder that the world we see is not always built from direct contact. Sometimes, even what feels invisible carries the trace of what is real, revealing images that seem to come from nowhere at all. Imagine yourself looking at frost patterns forming across a window on a cold morning. At first, the glass is bare, perfectly smooth, but then tiny branches of ice begin to spread, choosing one direction over another, shaping intricate structures that could never be predicted from the emptiness before. In physics, a similar idea explains how the universe itself may have taken shape. At the smallest scales, nature once held perfect symmetry. Forces were balanced, particles indistinguishable, the cosmos in its earliest state without preference. But then, through a process called symmetry breaking, that balance shifted. Tiny differences emerged, and those differences determined the structure of everything that followed. The concept is central to modern physics. In the first fractions of a second after the Big Bang, the universe's forces, gravity, electromagnetism, the strong and weak nuclear interactions, may have been unified. As the universe cooled, symmetries cracked. Some particles gained mass, while others remained weightless. Matter triumphed over antimatter, leaving behind the stars and galaxies we see. From the smallest imbalance, the vast architecture of reality was built. Without those breaks, the universe might have remained a featureless haze, with no atoms, no planets, no life to observe it. Daily life offers gentle metaphors. Imagine a perfectly balanced coin standing on its edge. In theory, it holds symmetry between heads and tails, but a breath of air or the faintest vibration tips it one way, and that tiny choice defines the outcome. Or, picture a row of dominoes where the very first nudge determines the pattern that follows. In each case, it is the smallest departure from balance that decides the entire course ahead. Symmetry breaking at the quantum scale is both delicate and decisive. It reminds us that perfection is not always fertile, that creation often requires imbalance, and structure grows from subtle departures. As you watch the frost forming on the glass, spreading into patterns from what began as stillness, you may sense the quiet echo of the universe itself. Vast order, born from the smallest cracks in symmetry. Imagine trying to hear the faintest whisper in a crowded room, or feel the brush of a single feather against your skin. Our senses, and even our most advanced classical instruments, eventually reach limits where noise drowns out signal. Yet quantum mechanics opens a way past those boundaries. Quantum sensors take advantage of superposition, entanglement, and interference to detect what would otherwise remain hidden. Tiny magnetic fields, gravitational waves, even single molecules. They operate not by overpowering the noise, but by reshaping how measurement itself is done. One approach uses entangled particles, whose shared state is more precise than any one particle alone. Measuring them in tandem sharpens sensitivity, like tuning two violins so perfectly that even the faintest discord becomes noticeable. Another technique, squeezed light, reduces uncertainty in one property of photons while increasing it in another, concentrating precision where it matters most. The result is an ability to push past the standard quantum limit, the boundary once thought unbreakable. Already, quantum sensors are reshaping technology. Atomic interferometers can detect subtle shifts in gravity, mapping underground structures without digging. Magnetometers based on quantum effects can trace the firing of neurons inside the brain, offering new ways to study thought itself. In space, quantum-enhanced instruments may one day chart the faint tug of dark matter or the sway of distant planets. In daily life, you might compare it to sharpening your vision so that shadows reveal details, or slowing your heartbeat until you hear sounds normally lost in silence. The instruments do not simply amplify, they attune themselves to the structure of the universe at its quietest levels. The paradox lies in this reversal. Quantum mechanics is often described as uncertain, a realm of chance. Yet here it becomes the source of certainty, a way to measure the nearly immeasurable. What once hid beneath the threshold of perception now rises into view, revealed not by brute force, but by listening to reality in its own language. Imagine yourself walking across an empty plain at dusk, the horizon stretching endlessly in all directions. Now, picture a single thread pulled tight across the sky, impossibly thin, yet infinitely long. humming softly like a string under tension. This image captures the essence of cosmic strings, hypothetical filaments that may have formed in the earliest moments after the universe began. Some theories suggest these strings are not ordinary matter at all, but relics of quantum fields, carrying with them properties that still ripple through space and time. A cosmic string would be unimaginably narrow, thinner than an atom, yet so dense that a single mile of it could outweigh mountains. Like seams stitched into the fabric of the cosmos, these strings might bend light, distort space, and subtly guide the shape of galaxies. And while they remain theoretical, they offer a bridge between the quantum and the cosmic, whispers of quantum properties stretching across the universe itself. Ancient stories often imagine the world bound together by invisible cords, threads of fate, or ropes tying heaven to earth. Science transforms these myths into quiet possibilities, where filaments of the early universe may still hum in silence, holding echoes of creation. As you drift with this thought, imagine the night sky not as empty, but woven with hidden strings, delicate, endless, and humming with quantum memory. Imagine yourself watching a craftsman carve patterns into wood, each careful cut shaping how the whole design will unfold. In a similar way, logic gates are the small tools that shape the flow of information in computers. In classical machines, they take the form of switches, turning signals on and off, guiding zeros and ones into patterns that build everything from calculators to entire networks. But in the quantum world, the gates that guide information must obey stranger rules. Quantum logic gates are the building blocks of quantum computation, and instead of controlling definite signals, they control fragile superpositions and entanglements. A classical gate says yes or no, 1 or 0. A quantum gate, however, can guide a qubit, a quantum bit, into many states at once. Through precise operations, these gates rotate probabilities, intertwine states, and even link particles across distances through entanglement. Imagine a coin not only flipping in the air, but also spinning so that it is both heads and tails until you finally catch it. A quantum gate controls that spinning uncertainty, allowing it to be harnessed for calculation. What makes this so powerful is scale. A handful of qubits linked through quantum gates can process information in ways that would overwhelm even the fastest classical supercomputers. Problems that would take centuries to solve through traditional methods could, in theory, be approached within hours or minutes. The gates themselves are not physical doors, but carefully engineered operations carried out through lasers, magnetic fields, or superconducting circuits. Each method a different way of coaxing fragile qubits to follow instructions without collapsing their delicate states. Quantum logic gates remind us that computation is not just about machinery, but about the rules we use to guide possibility. Instead of forcing reality into fixed answers at every step, these gates allow ambiguity to persist, shaping it into useful outcomes at the very end. They are not only tools of technology, but quiet demonstrations that even uncertainty can be guided, sculpted, and made into patterns that carry meaning. Imagine placing a small object above a magnet and watching it hover, perfectly still, as though gravity itself has been paused. In ordinary life, hovering requires effort, air currents, engines, or invisible strings. Yet, in quantum physics, there is a phenomenon known as quantum levitation, where objects appear to float effortlessly, locked into place above magnetic tracks. The effect arises from superconductors, materials cooled to extremely low temperatures. At that point, they expel magnetic fields from their interior, a behavior known as the Meissner effect. But when thin films of superconductors trap some of the field inside tiny imperfections, the object becomes pinned in space, a state called quantum locking. Instead of sliding freely, it hovers with uncanny stability, able to glide smoothly along curves or even remain frozen upside down. To picture this, imagine a train gliding above its tracks without wheels, held in place not by physical contact but by invisible constraints. Unlike balancing an object delicately on a point, this locking provides a firmness that resists nudges, making the levitation appear both natural and unshakable. In demonstrations, superconducting disks have been shown racing around magnetic circuits like miniature flying carpets, guided by fields rather than rails. The same principle underlies visions of frictionless transport, where high-speed trains could glide silently with minimal energy loss. For us, quantum levitation is more than a curiosity. It is a reminder that even gravity and magnetism, forces that seem so solid in daily life, can be bent by the subtle rules of quantum mechanics. Hovering above the ordinary, it hints at a world where the impossible becomes not spectacle, but quiet, stable reality. Imagine yourself watching two sets of ripples on a still pond. One is formed by a pebble dropped from your hand, the other by a leaf falling gently from a branch. Where the ripples meet, they do not simply add together. Some peaks rise higher while others cancel, leaving patches of calm. In physics, this familiar dance of waves becomes far stranger when it appears in the quantum world. Particles, tiny, solid-seeming points of matter, create interference patterns as though they were waves, overlapping in ways that defy the rules of classical explanation. The double-slit experiment remains the clearest window into this mystery. Fire electrons one by one at a barrier with two narrow openings, and instead of landing in two neat clusters, they form a striped pattern of light and dark, like ripples colliding on water. Each electron seems to pass through both slits at once, interfering with itself. Yet the moment you try to measure which slit it actually takes, the pattern vanishes, and the electrons behave like ordinary particles again. Observation collapses the wave, forcing reality to decide. Daily life offers no perfect analogy, but faint echoes appear in sound and light. A pair of violins playing the same note produces rich harmonies, sometimes amplifying, sometimes softening. Two beams of light overlap to create bright bands and dark shadows. Yet unlike music or light, which we can still trace back to clear causes, quantum interference resists such comfort. It is not merely the blending of waves, but the superposition of possibilities, each one equally real until measured. The result is a picture of reality that is both delicate and unsettling. The world we see may rest upon hidden layers where particles are not things but overlapping probabilities, weaving patterns beyond our direct perception. As you imagine those ripples spreading across the pond, colliding and fading into stillness, you may sense the quiet suggestion that reality itself is written in patterns we can glimpse but never fully explain. Imagine a crystal held in your hand. Its atoms line up in repeating patterns, forming a lattice that stretches across space in perfect symmetry. Now, imagine a structure that does not just repeat in space, but in time itself. This is the idea of a quantum time crystal, a system whose state changes in a regular rhythm, endlessly cycling without using or losing energy. To our intuition, this feels impossible. Motion usually fades, energy disperses, and perpetual motion is forbidden. Yet, in the strange rules of quantum mechanics, time crystals quietly break this expectation. The concept, first proposed by Nobel laureate Frank Wilczek in 2012, seemed almost heretical. A time crystal would be matter that never truly settles, oscillating forever in its lowest energy state. In classical physics, once you reach the ground state, the system rests in stillness. But in quantum physics, the ground state can still carry hidden motion, repeating like the steady tick of a clock, without ever winding down. Experiments in recent years, using trapped ions and superconducting qubits, have offered glimpses that such structures may indeed exist. Daily life offers few comparisons, though you might imagine a pendulum that never slows, or a heartbeat that continues without consuming strength. The motion is not powered from outside, but written into the symmetry of the system itself. Time crystals are not machines violating physics, but states of matter revealing that our understanding of time and order is incomplete. Their implications are vast. If time crystals can be harnessed, they may improve quantum computers, stabilizing information across endless cycles. More deeply, they challenge our picture of time as a straight line moving forward. Instead, time itself might contain patterns, rhythms echoing beneath reality. The paradox rests in its quiet defiance. Even at the lowest point of energy, where all should be still, the universe finds a way to keep moving, whispering that time may hold secrets yet unseen. Imagine yourself standing in a quiet valley at night, looking up at the sky. The stars appear fixed, yet their light has already been bent and shaped on its journey to you. Gravity, as Einstein described, curves space itself. Guiding starlight like a river bends around stone. But some theories suggest this bending may not be entirely smooth. On the smallest scales, gravity may carry quantum traits, causing light to shimmer, scatter, or shift in ways we cannot yet see. This is the mystery of quantum gravity lensing. Think of a medieval artisan shaping glass for a cathedral window. To the eye, the glass is clear, but under sunlight, tiny imperfections scatter the light into colors and patterns. In a similar way, space-time may not be perfectly smooth. It may have a grain, a quantum texture invisible to us, but able to nudge light in subtle ways. Photons crossing vast distances could carry these hidden signatures, whispers of quantum gravity etched into their path. Stories across cultures once imagined the heavens as veils, pierced or folded to reveal hidden truths. Modern science echoes this idea, that the universe itself may act as a lens, shaped not only by mass and motion, but by quantum rules written deep in space-time's fabric. As you drift with this thought, imagine every star's light as a traveler across a rippling tapestry, its path gently bent not only by gravity, but by the quiet grain of the quantum universe. Imagine yourself standing before a hologram in a museum, a flat sheet of glass that seems to hold the depth of a three-dimensional image. You tilt your head, and the perspective shifts, revealing more than should be possible from such a thin surface. Physics suggests something even stranger may be true of the universe itself, that all the information we see in 3 dimensions may be encoded on a surface, like a cosmic hologram projecting reality outward. This is the idea of the holographic principle. The roots of this vision lie in black holes. When matter falls into one, information about it seems lost, swallowed by the singularity. But Stephen Hawking and others found a puzzle. The amount of information a black hole can contain is not proportional to its volume, as one might expect, but to the area of its event horizon, the surface surrounding it. In other words, the storage of reality depends on surfaces, not depths. From this, some physicists have suggested that the whole universe may work the same way. What we perceive as a vast three-dimensional cosmos could, in some sense, be the unfolding of data written on a distant boundary. This does not mean our world is an illusion in the ordinary sense. Rather, it suggests that the deepest laws of physics may describe information in 2 dimensions, with the 3rd dimension emerging as a kind of projection. Like a hologram, what we see feels solid, detailed, and 3-dimensional, yet its essence could be inscribed on a surface beyond our view. For daily life, the thought is unsettling but also strangely comforting. Imagine every star, every planet, every thought, encoded not in unreachable depths, but etched upon the universe's boundary, as if the cosmos itself carried its own record. Whether or not this principle is ultimately proven, it offers a reminder that reality may hold more subtle layers of structure than the eye can ever perceive, patterns hidden not in the spaces we cross, but in the very edges that surround them. Imagine trying to weigh a feather on a scale meant for stones. The act of measuring is too heavy-handed, crushing what you meant to observe. In quantum physics, the same problem arises. Measurements often collapse fragile states, destroying the very information we hope to find. Yet there is a peculiar method called weak measurement, where the disturbance is softened so much that the system is only gently nudged. From this comes a surprising result: weak values, averages that sometimes fall outside the range of what seems possible. In practice, physicists prepare a particle in one state, apply a weak measurement, and then select only certain final outcomes. The numbers that emerge are not ordinary averages. they can appear exaggerated, even lying beyond the limits of the particle's defined values. It is as if a thermometer briefly suggested that water was hotter than boiling and colder than freezing at the same time. To picture this, imagine watching a crowd from afar. Each person's words reach you faintly, incomplete. But when you piece the fragments together, the conversation takes on a strange emphasis, as though whispers carry meanings never spoken. In weak values, these whispers reveal aspects of quantum systems that ordinary measurements cannot touch. Though debated, weak values have been used to amplify tiny signals and probe quantum paradoxes more closely. They hint at a deeper structure, where information exists in a liminal state between certainty and impossibility. For us, they offer a quiet reminder: not all truths fit neatly within expected bounds. Sometimes, by listening lightly instead of pressing firmly, reality speaks in voices stranger and subtler than we imagined. Imagine yourself in a quiet study, a desk lamp casting a soft glow across scattered pages of notes. You trace the lines of a neural network diagram, the web of connections resembling roots beneath a tree. In the classical world, these networks already form the foundation of artificial intelligence, learning patterns from vast amounts of data. But when combined with quantum processors, something new begins to emerge: quantum neural networks, systems capable of learning with a speed and depth that stretches far beyond the imagination. In ordinary computers, information moves through bits, a rigid sequence of ones and zeros. Quantum systems, however, work with qubits, existing in superposition, able to hold many possibilities at once. This means a single step in a quantum neural network can explore countless pathways simultaneously, rather than one at a time. Where classical learning may take years of computation, its quantum counterpart could unfold in moments, as though the machine were sifting through entire libraries in a single glance. Daily life offers only faint analogies. Imagine a traveler at a crossroads, choosing one path and then another, slowly mapping the terrain step by step. Now imagine that same traveler able to walk every path at once, returning with a complete map already drawn. Or think of water flowing not through a single channel, but through every crack and pore of a stone, spreading effortlessly to fill its shape. In each case, what would take immense time collapses into a single gesture. The implications are profound. A system that can learn at such speeds may solve problems in medicine, climate science, or cryptography that now seem unreachable. Yet the very idea raises questions as well. If intelligence can accelerate beyond our comprehension, what role remains for human understanding? As you sit in that quiet study, watching the lamplight soften across the diagrams, you may sense the paradox at hand. In the silence of quantum mechanics, even thought itself may learn to move with the swiftness of light. Imagine speaking into a canyon and hearing your own voice return as an echo. The sound was created in the past, yet it lingers into the present, shaping what you hear now. In quantum mechanics, something even stranger can occur. Systems where the past does not just leave traces, but actively loops back, influencing present outcomes. This is the puzzle of quantum delayed feedback, a phenomenon where earlier states affect measurements now, weaving cause and effect into a subtle circle. In classical physics, feedback loops are familiar. A thermostat switches off when a room warms and switches on again when it cools, creating balance. But quantum delayed feedback is more elusive. Here, particles in superposition evolve, interact, and sometimes feed information back into themselves after a delay. Imagine a photon traveling through an optical circuit that allows part of its state to circle back and meet itself later. The measurement you perform does not only reflect the now, but also the echoes of what the system once was. The particle's past is braided into its present. Laboratories have begun experimenting with these effects using superconducting qubits and photonic loops. The results show that delayed feedback can stabilize fragile quantum states, extending their lifetime beyond what would normally be possible. It is as though the system whispers reminders of its earlier self, keeping its present aligned. At the same time, the loops introduce paradoxes, blurring the line between cause and effect. Did the system's state arise from its present conditions, or from a message it received from its own past? Daily life struggles to offer a perfect analogy, but you might imagine writing a note to yourself, sealing it, and then receiving it before you finished writing. The message is both from the past and yet intertwined with your present choices. The paradox is quiet but unsettling. In the quantum world, time need not flow in straight lines. The present is not simply what follows the past. It may also be what the past remembers of itself. Imagine yourself gazing into a mirror. The reflection looks the same, left and right reversed, yet perfectly balanced. For centuries, scientists assumed nature itself obeyed this symmetry, that the laws of physics would remain unchanged if flipped like a mirror image. But in the quantum world, not everything plays along. Certain particles break this expected rule, behaving differently from their mirrored counterparts. This quiet rebellion is called parity violation. Think of a medieval mason carving an arch. Each side mirrors the other, stone for stone, creating strength through balance. Now imagine if one side subtly refused to follow the pattern, its lines leaning just slightly away. The arch would still stand, but its hidden imbalance would reveal a deeper truth. In physics, parity violation showed up most clearly in the behavior of weak nuclear forces, where particles seemed to prefer one-handedness over the other, shattering the belief that nature was perfectly symmetrical. Cultures have long told stories of mirrored worlds, twin realms that should reflect each other, yet do not. Parity violation echoes this theme, showing that even at the smallest scales, the universe is not a flawless reflection. It carries preferences, small tilts, hidden biases written into its rules. As you rest with this thought, imagine holding a mirror to reality itself, only to find the reflection is not quite the same. The symmetry falters, and in that quiet break, the universe reveals its hidden asymmetry. Imagine yourself watching a craftsman slowly cool molten glass, letting the material settle into its most stable form. This careful process of heating and cooling is known as annealing, and it has been used for centuries to guide materials into order. In the world of computation, a similar idea appears in solving optimization problems, finding the best solution among countless possibilities. But in the quantum realm, annealing takes on a far stranger form. Quantum annealing uses the peculiar rules of quantum mechanics to allow a system to fall into its lowest energy state, revealing answers to problems that classical computers struggle to touch. In optimization, the challenge is like searching for the deepest valley in a landscape filled with countless hills and ridges. A classical computer explores the terrain step by step, moving downhill, sometimes becoming trapped in smaller valleys that are not the true minimum. Quantum annealing, however, uses tunneling, the ability of particles to pass through barriers rather than climb them. Instead of slowly crawling across the landscape, the system can slip through the ridges, reaching the deepest valley directly. What might take a traditional machine thousands of trials can, in principle, be found almost instantly through quantum effects. Already, companies have built machines designed for this purpose, though their capabilities remain under study. These devices are not general quantum computers, but are tailored to optimization, handling tasks such as scheduling, logistics, or even the design of new materials. Though still in their infancy, they hint at a future where quantum mechanics will not only describe the world, but also help us navigate it more efficiently. For daily life, the image of problems solving themselves may feel almost magical, as though answers could emerge without effort. Yet, it is not magic, but physics, the ability of matter at its smallest scales to explore possibilities in ways our larger world never allows. Quantum annealing reminds us that hidden within the rules of uncertainty lies a quiet efficiency, a path where the universe itself seems to lend a hand in choosing the best way forward. Imagine sunlight streaming through a window, the beams appearing straight and steady as they fall across the floor. Light feels simple, photons moving in lines, illuminating the world. Yet in the quantum realm, photons can be shaped into far more intricate forms. They can be twisted, carrying something called orbital angular momentum, as though the light itself were spiraling through space. This twisting turns an ordinary beam into a kind of corkscrew, with each photon tracing a helical path. In the laboratory, scientists use special devices to shape light in this way, creating beams that look like rings or spirals instead of smooth spots. The photons in such beams carry extra information in their twisted states, opening possibilities for communication and imaging. Unlike the two simple states of polarization, orbital angular momentum offers a vast spectrum, each twist a new channel, multiplying how much data a single beam of light can hold. To picture this, imagine a river. Normally, the current flows straight downstream, smooth and predictable. But under certain conditions, the water begins to swirl, forming eddies and spirals, each with its own rhythm. Twisted light behaves much the same, carrying not just flow, but pattern. Applications stretch from quantum cryptography, where twisted photons could secure messages, to astronomy, where they might sharpen the view of distant stars. For us, it reveals how even something as familiar as light still holds hidden depths. Beneath its apparent simplicity lies an elegance of structure, beams that not only shine, but spiral, carrying with them the quiet signature of quantum possibility. Imagine yourself watching two dancers on a quiet stage, their movements so perfectly in tune that one seems to anticipate the other's every gesture. Entanglement in quantum mechanics is a bit like this. Two particles linked so deeply that measuring one instantly shapes the state of the other, no matter how far apart they may be. Yet there is an even stranger possibility, hyperentanglement, where particles are not bound by a single connection, but by many, entangled across several properties at once. Ordinary entanglement might tie particles by their spin or their polarization, but hyperentanglement weaves multiple threads together. A pair of photons, for instance, could be entangled in polarization, momentum, and spatial mode simultaneously. Measuring one particle in any of these dimensions reveals information about the other, as if they share a secret language layered in many voices at once. Experiments with hyper-entangled states began in the late 20th century, offering new possibilities for quantum communication, teleportation, and computing, systems that require immense complexity yet thrive on these deeper, multidimensional bonds. Daily life offers only faint metaphors. Imagine two musicians playing across a distance, not only matching tempo, but also pitch, timbre, and rhythm, every element of their performance linked. Or, think of twins finishing each other's sentences while also mirroring tone, expression, and thought, a unity that seems to reach across layers of experience. In each case, the connection is not one-dimensional, but woven through many aspects at once. The phenomenon of hyperentanglement reminds us that nature's bonds are not always simple or singular. Reality allows for connections layered so deeply they seem inexhaustible, each thread reinforcing the others. As you picture those two dancers moving in perfect unison, not only step for step, but breath for breath, you may sense the quiet suggestion that the universe itself is bound together in ways far richer and far more mysterious than our ordinary senses can ever perceive. Imagine watching a soap bubble shimmer in the air. For a moment it reflects every color, fragile and undecided, before it bursts into a single drop. In quantum mechanics, the wave function is like that bubble, delicate, containing many possibilities at once. Standard theory tells us that when a measurement is made, the wave function collapses instantly, reducing the blur of probabilities to one outcome. But what if that collapse is not immediate? What if the transition itself stretches across time, unfolding gradually like a fading echo? This is the puzzle of collapse delay. Some experiments have hinted at this possibility. When photons or atoms are measured with extraordinary precision, the results can show a brief ambiguity, as though the system hesitates before settling. The particle is neither fully collapsed nor fully spread out, caught in a twilight zone between potential and certainty. If collapse takes time, it means reality is not a sharp switch, but a process, slow enough in principle to be studied and perhaps even influenced. The implications ripple outward. Quantum computers depend on keeping states alive before collapse finalizes them. If collapse can be delayed, engineers might extend coherence times, protecting fragile information from vanishing. Philosophers, meanwhile, wonder what this means for the nature of reality. If the wave function lingers before choosing, is the universe itself undecided during that span? Daily life offers no perfect comparison, but you might think of a coin spinning in the air. It has not yet landed, yet for an instant you see it shimmering, both heads and tails at once. Imagine if the landing itself stretched in slow motion, a long hesitation before the outcome is revealed. The paradox of collapse delay is gentle but haunting. It suggests that even the most fundamental event in quantum theory, the moment possibility becomes reality, may not be abrupt. Instead, it may arrive as a slow drift, a soft closing of doors one by one until only a single path remains. Imagine yourself walking through a foggy forest path at night. Each step you take is deliberate, left or right, forward or back, and the path behind you tells a clear story. But in the quantum world, a particle's journey is far stranger. Instead of following one fixed route, it can explore many paths at once, weaving a tapestry of probabilities before settling into a single outcome. This wandering is known as a quantum random walk. Think of a medieval messenger carrying a letter across winding village roads. He may choose one route today, another tomorrow, but always a single trail. Now imagine a version where he takes every possible road simultaneously, his footsteps spread across all choices, yet somehow converging at the same destination. For particles, this is not just imagination, but a way they truly behave, steps scattered across probabilities until measured. Ancient tales often spoke of travelers crossing crossroads that led to many destinies, each choice real in its own way. Quantum random walks echo that vision, where uncertainty is not error, but a pattern, a rhythm of possibilities unfolding. As you rest with this thought, picture each particle as a quiet traveler in the fog, its path both many and one, its steps uncertain yet guided by a hidden order. The randomness is not chaos, but a delicate dance of probabilities shaping the world you see. Imagine yourself standing in a library filled with countless books. If you searched in the ordinary way, you would open one volume at a time, reading line by line, moving slowly toward the answer you need. This is how classical computers solve problems, step by step, testing one path after another. But quantum systems follow a different rhythm. Through a principle called quantum parallelism, they can explore many possible solutions at once, as though the entire library had been read simultaneously in silence. At the heart of this ability is superposition. A quantum bit, or qubit, does not settle into 0 or 1 until it is measured. Instead, it holds both possibilities at once, and when many qubits are linked together, their combined state contains an immense range of outcomes. A carefully designed quantum algorithm can guide these superpositions, allowing the computer to weigh countless potential answers in parallel before collapsing into a result. It is not that the machine tries every possibility one by one. It is that quantum rules let it sample them all together, compressing what would be impossible into a single unfolding. This advantage is not universal. Quantum computers are not faster for every problem, but for certain tasks, factoring large numbers, simulating molecules, searching enormous datasets, the ability to explore solutions in parallel offers leaps in efficiency that classical machines could never match. It is like asking 1,000 travelers to walk every road, yet somehow receiving all their reports at the same instant. For daily life, the idea may feel abstract, but its consequences are profound. The medicines of the future, the design of new materials, the secure communications we rely on, all may one day depend on this ability to let quantum states do their quiet work across many paths at once. Quantum parallelism is not only a technological advantage, It is a reminder that at the foundations of reality, possibility itself is the raw material from which answers emerge. Imagine standing in the stillness of open space, surrounded by what seems to be perfect emptiness. In ordinary thought, a vacuum is nothing at all, no matter, no air, no resistance. Yet quantum physics tells us that even empty space is restless, filled with flickering fields and virtual particles that appear and vanish in silence. Under extreme conditions, this vacuum can act like a medium, bending the path of light itself. This subtle phenomenon is called quantum vacuum lensing. The effect arises because the vacuum is not truly void. Quantum electrodynamics predicts that when light passes through intense electromagnetic fields, the virtual particles of the vacuum can momentarily polarize, creating a kind of refractive index. In essence, the empty background behaves like glass, gently curving or twisting beams of light. Though the effect is vanishingly small under everyday conditions, it becomes meaningful near extraordinary environments, like neutron stars, whose magnetic fields are billions of times stronger than anything we can produce on Earth. To imagine this, picture looking through heat rising from a desert floor. The air shimmers, bending the view of distant shapes, distorting horizons. In vacuum lensing, the distortion does not come from heat or air, but from the fabric of space itself, stirred by invisible fields. Astronomers hope to observe these effects directly in the polarized light from magnetars, where vacuum lensing may leave subtle imprints. For us, it is another reminder that even what we call nothing is not truly empty. Beneath the silence of the void lies a medium alive with potential, capable of guiding light in ways our senses alone could never reveal. Imagine yourself handling a fragile glass ornament, its surface so thin that even the faintest touch could leave a mark. Quantum states are much like this, delicate, easily disturbed by their surroundings. A stray vibration, a tiny shift in temperature, even the faint presence of measurement can collapse the superpositions that make them unique. For a long time, this fragility seemed to limit the promise of quantum computing. If information written in qubits could vanish so easily, how could it ever be used? The answer emerged in the form of quantum error correction, a way to protect the delicate without breaking it. In classical computers, error correction is straightforward: add redundancy, repeat the signal, and detect mistakes. But in the quantum world, duplicating a state is impossible. The no-cloning theorem forbids it. Instead, scientists found a subtler method, spreading information across multiple qubits, so that even if one is disturbed, the overall pattern can still be recovered. The system works less like copying a fragile note and more like weaving it into a tapestry, where no single thread holds the whole, yet all together preserve its meaning. Daily life offers echoes of this quiet resilience. Imagine a melody carried not by one musician, but by an entire orchestra. If one instrument falters, the music continues. Or think of a story remembered by a community. Even if one voice forgets a detail, the others carry it forward, keeping the tale alive. In each case, the fragility of one part is offset by the strength of the whole. Quantum error correction is still a work in progress, but its principle is reassuring. Even in a realm defined by fragility, there are ways to preserve order, to protect meaning against chaos. As you imagine that glass ornament glowing softly in your hands, you may sense the deeper lesson. With enough care and structure, even the most delicate states of reality can endure. Imagine a crystal cooled to absolute zero. At that temperature, motion should cease, atoms should freeze into perfect stillness, and the system should reach its most stable, ordered state. Yet in the strange world of quantum mechanics, not everything behaves as expected. In a phase of matter known as a quantum spin liquid, the spins of electrons refuse to settle. Even at absolute zero, they remain in constant fluctuation, weaving patterns of entanglement that never lock into place. The lattice holds, the material is solid, but beneath its structure, the magnetic order is forever restless. The name liquid does not mean the substance flows like water, but that its magnetic orientation never crystallizes. In ordinary magnets, spins align into order, north and south, up and down, forming predictable patterns. In spin liquids, frustration prevents this. The geometry of the lattice forces spins into competing arrangements that cannot be satisfied at once, so the system chooses none. Instead, it enters a quantum dance, a fluid state of correlations that ripple endlessly. For physicists, this phase is fascinating because it gives rise to emergent phenomena. Quasiparticles known as anyons may appear, carrying fractions of an electron's properties. These elusive excitations could become building blocks for fault-tolerant quantum computers, encoding information in ways resistant to noise. Spin liquids may also shed light on high-temperature superconductors, where electrons pair up in unexpected ways. Daily life offers no perfect analogy, but you might imagine a room of dancers who never fall into a single formation. Each dancer's step depends on the others, yet the choreography never repeats, never resolves. The motion continues without end, even though the music has stopped. The paradox is subtle, yet profound. At the coldest, quietest point imaginable, where all should be frozen, a hidden motion persists. Quantum spin liquids remind us that matter is not always what it seems, and that even in stillness, the universe may be endlessly alive. Imagine yourself sitting beside a river, watching leaves drift on the surface. At first, their movement seems separate, each carried by its own current. Then, unexpectedly, two leaves turn in the same direction, as though guided by a hidden rhythm beneath the water. In the quantum world, such alignments happen often, separate events, distant or unrelated, falling into mysterious harmony. This quiet coordination is sometimes described as quantum synchronicity. In daily life, we notice small echoes of this. A medieval clockmaker, for instance, might hear two pendulums swinging on opposite sides of his workshop, only to find them eventually ticking in unison. He cannot see the subtle vibrations linking them through the wooden beams, yet the harmony emerges all the same. Quantum laws suggest similar unseen threads, where particles or events separated in space can align outcomes, not through obvious cause, but through the deep structure of probability itself. Cultures have long carried myths of coincidences that feel guided, omens, patterns in the stars, or destinies weaving together. Science gives no mystical explanation, but quantum mechanics reminds us that synchronicity can arise from rules too subtle to notice, shaping what seems accidental. As you rest with this thought, imagine reality as a wide river of events. On the surface, they appear scattered, but beneath flows a hidden current, gently aligning them in ways we cannot see. Imagine yourself sitting in a quiet room, sunlight pooling across the floor, the world around you seemingly stable and definite. A chair is a chair, a shadow is a shadow, and nothing about their presence feels uncertain. Yet, in quantum mechanics, particles often resist such clarity. They linger in superpositions, many possibilities layered together, until something intervenes. In the traditional view, it is observation or measurement that forces the system to choose, collapsing the haze of possibilities into a single outcome. But some theories suggest collapse does not wait for an observer at all. It may happen naturally, woven into the fabric of reality itself. These approaches are known as objective collapse theories. Instead of requiring a conscious observer, they propose that wave functions decay spontaneously over time, or that large systems cannot sustain superposition beyond a certain scale. One model, for example, suggests that particles above a critical mass undergo collapse automatically, as though the universe itself insists on stability. Another ties collapse to gravity, proposing that space-time resists being in multiple states at once, forcing a resolution without the need for measurement. If this is true, then quantum uncertainty is not held in suspense until we look. It unravels gradually on its own, with observation playing no special role. The moon does not exist only when we see it, nor do distant galaxies wait for a telescope to come into view. Their definiteness emerges quietly, as a natural process of the universe. For daily life, this idea is both subtle and reassuring. It reminds us that reality may not depend on our awareness to take shape. The solidity we trust, the ground beneath our feet, the objects in our hands, may not be the product of perception, but of deeper rules that collapse possibilities into facts. In this view, the world is always choosing, even in the silence where no one is watching. Imagine writing a letter and sending it to a single friend. To share it with others, you'd need to copy it again and again, each page faithfully reproduced. In the quantum world, things are not so simple. A particle's state cannot be perfectly copied because observation itself changes it. Yet there exists a curious process called quantum telecloning, where information about a quantum state can be shared among several locations at once, not as exact duplicates, but as distributed echoes. The principle builds on two ideas: entanglement and quantum teleportation. In teleportation, the state of a particle is transferred from one place to another using entangled partners and classical communication. Telecloning extends this further. Instead of sending the state to one destination, it spreads approximations to multiple recipients simultaneously, like ripples moving outward from a single stone dropped into water. Each clone is imperfect, but together they preserve the essence of the original. To imagine this, think of a storyteller speaking in a quiet hall. No one listener hears every word exactly as it leaves the speaker's mouth, yet the story carries across the room, received in many ears at once. In telecloning, the story of the quantum state is distributed, shared across space without ever being directly copied in the classical sense. Experiments have begun to demonstrate telecloning with photons, hinting at future networks where quantum information is not just transferred, but shared widely. For us, it is a reminder that the language of information at the quantum level is far subtler than simple duplication. Instead, it echoes and disperses, creating a strange harmony of many voices drawn from one source. Imagine yourself sitting at a table with a simple puzzle in front of you. The rules are clear, the strategies straightforward, and you know that with enough effort, the solution will come. In the classical world, games work this way. Moves are made locally, choices follow cause and effect. But in the quantum world, particles appear to play games according to strategies no classical system could ever achieve. These are called quantum non-local games, where outcomes are linked across distance, as though players share answers through invisible channels. The roots of this idea lie in experiments with entanglement. Imagine two particles separated by light years, yet still coordinated in their responses when measured. When framed as a game, each particle seems to give answers that no classical rulebook could allow, but that quantum mechanics predicts with precision. Bell's theorem formalized this in the 1960s, showing that no local, hidden set of instructions could explain the results. The particles are not communicating in any normal sense, but their correlations win the game with a success rate impossible in a classical world. Daily life offers only distant echoes. You might imagine two friends taking a test in separate rooms, yet their answers always match in just the right way, beyond any possible prearranged plan. Or think of two musicians improvising from different cities, yet producing harmonies as though they share the same unseen rhythm. These metaphors capture the strangeness, but the quantum version is deeper. The coordination arises not from planning, but from the structure of reality itself. Quantum non-local games are more than curiosities. They are tools for probing the foundations of physics and building new technologies in quantum communication. But they also carry a quieter message. The universe, at its deepest level, does not always follow the strategies we expect. As you picture that simple puzzle on the table, you may sense the hidden suggestion. Sometimes the pieces fit together not because of visible moves, but because reality itself allows connections no classical game could ever permit. Imagine two people trying to share a secret across a noisy, dangerous channel. In the classical world, they might rely on complex mathematics, codes so intricate that breaking them would take centuries of calculation. But given enough time and power, even those codes could, in principle, be cracked. Quantum cryptographic keys promise something stronger, secrecy guaranteed not by difficulty, but by the laws of physics themselves. The foundation is uncertainty. In quantum mechanics, you cannot measure certain properties of a particle without disturbing them. If two people, often called Alice and Bob, exchange a string of photons prepared in carefully chosen states, they can build a shared key. Any eavesdropper who tries to intercept the photons inevitably leaves traces, because their measurement alters the states. When Alice and Bob compare notes on a subset of their photons, any tampering is immediately revealed. If the channel shows no disturbance, they know the rest of the key is secure, as unbreakable as reality will allow. This principle, known as quantum key distribution, has already moved from theory into practice. Satellites have transmitted quantum keys across continents, linking cities thousands of kilometers apart. Banks and governments are beginning to test it, exploring networks where the very act of spying exposes the spy. In daily life, it is as if you and a friend agreed on a code by whispering in a room that changes shape every time someone else tries to listen. The room itself ensures privacy. The paradox is gentle but striking. Uncertainty, usually a source of frustration, becomes the guardian of certainty. The same rules that prevent us from knowing everything about a quantum system guarantee that no secret can be stolen without leaving a mark. In this way, the fragility of quantum states transforms into strength, offering a glimpse of a future where information is protected not by walls of mathematics, but by the quiet, unyielding structure of nature itself. Imagine yourself in a quiet laboratory, the faint hum of instruments surrounding you, a superconducting wire stretched across the table. At first, the current flows perfectly, a smooth and unbroken river of electrons, each particle moving in perfect synchrony with its neighbors. This harmony is what physicists call phase coherence, a delicate rhythm that defines superconductivity. Yet sometimes, without warning, the rhythm stumbles. A single quantum fluctuation, a tiny, almost imperceptible disturbance, can cause a phase slip, and the flow momentarily falters. It is not a crash, nor a dramatic eruption, but a subtle pause, a fleeting loss of alignment. Imagine a line of dancers moving in unison, and then one small step misplaces the timing, briefly breaking the perfect pattern. These slips remind us that even in systems that seem perfectly ordered, quantum laws allow for sudden, unpredictable changes. They are rare, almost hidden, but their effects ripple through the material, like a whispered misstep felt across a vast, silent hall. The electrons resume their dance, and coherence returns, yet the memory of that brief disruption lingers, a quiet testament to the fragility beneath apparent perfection. As you reflect on this, picture reality itself as a vast network of rhythms, each layer of order susceptible to subtle slips, reminding us that even harmony is not absolute, and that the universe contains moments of stillness, pause, and gentle unpredictability. Imagine yourself watching two clocks tick side by side. Their rhythm feels steady, predictable. But now imagine moving one of them closer to a black hole. Time begins to stretch, slow, dilate. This is Einstein's time dilation, an effect of gravity and motion that has been measured and confirmed. But now imagine something subtler, a quantum system in superposition, existing in multiple states at once. Could time itself behave differently for each of those states? Could a particle experience time not as a single shared flow, but as a branching, layered phenomenon? This is the idea behind quantum time dilation. In certain interpretations, when a particle enters superposition, taking two or more paths simultaneously, its experience of time may diverge across those paths. One version of the particle may feel time pass more quickly, another more slowly, even if the whole system remains unified. These are not just thought experiments. Some researchers are designing tests with quantum clocks, atoms or photons that can mark time with extreme precision to observe whether superposed systems tick at different rates depending on their path through space or their gravitational environment. This raises deep questions. If time can stretch or compress, based on a quantum state, then what does it mean for something to age? What does it mean for a moment to occur? The steady beat we associate with clocks and calendars may be a surface-level experience, smoothed over countless microscopic timelines shifting subtly beneath it. In everyday life, time feels like a constant river, flowing forward. But on the quantum scale, that river may split and rejoin, ripple and stall, each thread of possibility running with its own tempo. A superposed particle may not just be in two places at once, it may be in two durations at once. Time, it seems, is not only relative to motion and gravity, but possibly also to choice, to uncertainty, to the unseen structure of possibility itself. Imagine walking through a dense forest where the path winds unpredictably, sunlight flickering through leaves. At first glance, it feels chaotic, every branch, every root placed at random. But step back far enough, and patterns begin to emerge. Symmetries, repetitions, a quiet order hidden in the seeming disorder. In quantum physics, something similar is suspected. Beneath the randomness of particles and probabilities, there may lie hidden symmetries, subtle mathematical patterns that govern how quantum systems behave. In classical physics, symmetry is often clear. A sphere looks the same from every angle. A snowflake holds balance in all directions. But in the quantum realm, symmetry becomes elusive. Particles don't have fixed positions, and outcomes are governed by probabilities. Yet when scientists study quantum systems more deeply, especially in the mathematics of quantum field theory, they find hints that unseen symmetries may be shaping what we observe. These hidden symmetries help explain conservation laws, particle behaviors, and even interactions between forces. In some cases, particles appear related in unexpected ways, as though they are reflections of one another across some invisible axis. To imagine it, think of hearing a melody on a piano, but only one note at a time, out of order. It seems random, until you recognize the pattern beneath. The harmony was always there, waiting to be heard in the right way. Quantum hidden symmetries are not yet fully understood, but they continue to guide research into unifying the forces of nature. For us, they suggest that behind the noise of the quantum world, there may be a deeper rhythm, subtle, concealed, but ever present, shaping reality from the shadows. Imagine yourself in a quiet observatory beneath a dark sky, watching starlight drift in from across the universe. The telescope before you obeys the rules of Einstein's relativity. How gravity bends light, how time slows under acceleration, how space and time stretch and fold. But in the tiniest parts of the universe, in the spaces between atoms and particles, another language is spoken, the language of quantum mechanics. These two systems, relativity and quantum theory, have guided physics for over a century, each deeply successful, yet strangely separate. And yet, beneath their surface, a quiet suspicion remains. They may be telling different sides of the same story. Relativity describes the large and the smooth. Planets, stars, galaxies, all move with elegant precision. Quantum mechanics, on the other hand, describes the small and the chaotic. Particles flicker in and out of states. Probabilities replace certainties, and observation alters the thing observed. Bridging these views has long been one of science's greatest challenges. Some theories suggest that spacetime itself may be emergent, rising out of quantum entanglement the way fabric rises from threads. Others imagine gravity as a side effect of quantum information, unfolding from the strange correlations between particles. Daily life offers only distant metaphors. You might think of two languages, one spoken in poetry, the other in mathematics, each describing the same feeling from a different angle. Or imagine a coastline viewed from the shore, then again from an airplane. Both perspectives are true, yet neither captures the whole. The search for connection continues. Experiments grow more precise, theories more refined. But the deeper hope is quiet and enduring, that the vast and the tiny, the cosmic and the quantum, are not separate realms, but two expressions of one underlying reality. And as you watch starlight arrive through the silence of space, you may feel that possibility settling in like dusk. The idea that everything, from the spin of a particle to the curve of a galaxy, is linked by patterns not yet fully understood, but waiting, patiently, to be seen. Imagine a black hole merger, two titanic objects spiraling toward each other in the silent theater of space. When they collide, gravitational waves ripple outward, carrying the story of that cosmic embrace across the universe. Yet, some physicists suspect there may be more. Subtle whispers after the main event, faint echoes that hint at the hidden structure of space-time itself. These echoes are not like sound in air. They are distortions in the very fabric of the universe, emerging after the primary gravitational waves have passed. In classical general relativity, a black hole swallows all, leaving nothing behind but its mass, spin, and charge. But quantum theories suggest that information may be preserved in ways we do not yet fully understand. The echoes could be signals of this information, trapped and then released, as if the black hole itself were hesitating, reluctant to fully forget what it has consumed. Researchers examine data from observatories like LIGO and Virgo, scanning for patterns in the fading tail of gravitational wave signals. The task is daunting. The signals are minuscule, drowned in cosmic background noise, yet even a whisper, if confirmed, could illuminate the interface between quantum mechanics and gravity, a realm where our current theories falter. Picture it in daily terms. A bell rings, its sound fading, but a faint resonance lingers in the air, almost imperceptible. That lingering tone carries clues about the bell's inner structure, its hidden harmonics. Similarly, black hole echoes might reveal the deep, underlying architecture of space-time, encoded in patterns we are only beginning to detect. The paradox is profound. From an object that should devour everything, hints emerge that it preserves secrets. In the quiet aftermath of cosmic collisions, the universe may whisper its most intimate truths, subtle vibrations that challenge our understanding of reality and remind us that even in ultimate darkness, traces of past events may persist, waiting to be heard. Imagine yourself floating in the vast quiet of the cosmos, where stars shimmer faintly against the dark canvas of space. Here, space and time, the very fabric of reality, may not be as separate as they seem. In the strange domain of quantum mechanics, they can become entangled, subtly connected across distances and durations, as if threads of an unseen web tie moments together. Picture two distant events, separated by light years, yet linked in a silent dialogue. A change in one instant echoes in another, not through force or signal, but through the shared quantum state of spacetime itself. It is a connection that defies ordinary intuition, a gentle reminder that what seems local and independent may, at the deepest level, be inseparably bound. Walking through this idea, imagine yourself tracing the curves of space-time like a delicate thread stretched across a loom, where tugging in one corner causes vibrations elsewhere, invisible but real. Time does not march alone, nor space drift freely. Each can influence the other in subtle, precise ways. These entanglements are not dramatic collisions or explosions. They are quiet, almost imperceptible, yet they hint at a universe more woven, more interconnected than everyday senses reveal. As you drift among these invisible connections, there is a sense of calm wonder, a reassurance that beneath apparent randomness lies a hidden, coherent rhythm binding all things. Imagine yourself floating in a quiet field, watching ripples spread across a still pond. Each wave carries shape and motion, but you know that the water itself is real. It's the substance underneath the ripple. In quantum mechanics, we describe particles not as solid points, but through wave functions, mathematical patterns that ripple through abstract spaces of probability. Traditionally, these wave functions are treated as tools, just a way to predict outcomes. But some physicists now ask, what if the wave function isn't just a calculation? What if it's real? This idea is called wave function realism. It suggests that the wave function isn't just a placeholder for ignorance, but a physical object in its own right, something woven into the fabric of the universe. When we say an electron exists in many places at once or holds multiple spins, the wave function describes this blend of possibilities. But in this view, it isn't just describing, it is the thing that exists. The rippling is not in our minds, it is in the world. This shifts how we see particles. They are not little dots hiding somewhere waiting to be discovered. They are better understood as waves of potential, patterns that only collapse into certainty under the right conditions. The particle is not hidden inside the wave function. The particle is the wave function, until something forces it to appear as a point. In daily life, we think of reality as made of things, objects we can see, touch, name. But wave function realism hints that reality might instead be made of patterns, not the solid bricks of classical matter, but shifting clouds of possibility. The world you walk through may be less like a set of objects and more like a melody, real, but flowing, unfolding, and resolved only when heard. So when you imagine a particle, try not to picture a marble on a table. Picture instead a ripple in something deeper, something quieter, something always there, an invisible wave guiding reality toward its next unfolding. Imagine standing before a mirror, watching yourself watching. In the classical world, this creates no paradox, just reflection, just perception. But in the quantum realm, the act of observation carries weight. It changes the system, collapses possibilities into outcomes. So what happens if a quantum system could, in theory, observe itself? This is the quiet puzzle of quantum self-observation, a scenario where the observer and the observed are not separate, but part of the same delicate web. In standard quantum mechanics, measurement is typically thought of as something done from the outside, an apparatus, a detector, a human experimenter. But some interpretations suggest that systems could internally register changes in their own states. It wouldn't be awareness in any ordinary sense, but an internal entanglement, where one part of the system acts as a measuring reference for another. In this view, the boundary between system and observer begins to blur. To picture this, imagine a book writing its own story as it reads each word. Each page influences the next, not through outside editing, but by a loop of internal reference, cause and effect folding inward. In the quantum case, this loop might subtly change the evolution of the system, hinting that observation is not always external interference, but sometimes quiet introspection. This idea remains speculative, but it has emerged in discussions of quantum information theory, especially when considering closed systems with no outside environment. It raises soft but profound questions. Is the collapse of a wave function always the result of something else looking in? Or can systems, in their own isolated silence, bring about change from within? For us, it is a whisper of possibility, that perhaps, in some fundamental way, the universe doesn't just unfold, but also watches itself unfolding. Imagine yourself standing at the edge of a still lake just before sunrise. From where you stand, the surface seems perfectly smooth, glassy, continuous. But if you kneel closer, your eyes just inches from the water, you begin to see movement, small ripples, shifting patterns, a restless texture invisible from afar. Some physicists believe that space-time itself may behave in much the same way. At the vast scale of stars and galaxies, it appears smooth, predictable. But deep down, near the Planck length, far smaller than an atom, space-time might not be smooth at all. It may be frothing, chaotic, something they call quantum gravity foam. The idea was first proposed by physicist John Wheeler, who imagined space-time at tiny scales as turbulent and constantly shifting. Instead of a flat canvas, it becomes a restless sea where distances blur, time wobbles, and tiny wormholes appear and vanish. This foam is not made of matter, but of fluctuations in the very fabric of space and time. Quantum uncertainty, combined with gravity, creates a landscape so unstable that our usual concepts of geometry no longer apply. Straight lines bend, clocks lose meaning, and the very idea of location may dissolve. Daily life has no real equivalent, but you might picture looking at a map drawn on water, where shapes pulse and flicker as you try to read them. Or imagine snow falling into a river, each flake briefly forming a pattern, then melting back into motion. The closer you look, the less certain the structure becomes. Quantum gravity foam is more than a curiosity. It represents a frontier. It hints at where general relativity and quantum mechanics might finally merge, where the deep code of the universe may be hidden. As you stand again beside the lake, watching the light gently shimmer on its surface, you may sense that even calmness can conceal complexity, that beneath the smoothness of space and time, something wild is always whispering. Imagine standing at the edge of a reality you think you know, where the rules seem stable and predictable. Quantum mechanics, however, hints that stability may be an illusion. At the tiniest scales, particles do not exist in one state alone. They occupy a spectrum of possibilities, a haze of probabilities, until measured. Some theorists speculate that if consciousness, intention, or observation can influence quantum states, then perhaps, in principle, it might influence which branch of reality we experience. In this view, every choice, every moment, is like a quantum fork in the road. The universe continuously unfolds into countless parallel outcomes, each a coherent world running alongside the others. While we navigate our familiar path, hidden corridors of possibility exist, overlapping, interweaving, just out of reach. The idea of reality shifting suggests that, under very subtle conditions, we might move along these corridors, stepping into an alternate branch where circumstances are slightly or dramatically different. Experiments with quantum superposition, entanglement, and interference demonstrate how fragile and fluid states can be. One measurement here, one entangled decision there, and the outcome is completely altered. It is as if the universe itself responds to the act of observation, bending probabilities in ways we are only beginning to map. In practical terms, reality shifting remains speculative, largely philosophical, and deeply mysterious. But it forces us to reconsider our most basic assumptions about the world, that it is fixed, singular, and inevitable. Picture it like a vast library of potential lives, each book slightly different. We read one story, experiencing its narrative as absolute truth, unaware that all other volumes exist simultaneously. Quantum reality shifting is the quiet suggestion that some subtle mechanism, hidden in the weave of probabilities, might allow us to move, ever so slightly, from one story to another. It is an invitation to imagine our existence not as a single path, but as a constellation of infinite possibilities, and to wonder whether the choice of which path we inhabit is, in some extraordinary way, not entirely out of our hands.